For centuries we thought it was nothing, a faint smudge in the night sky, a wisp of gas drifting somewhere inside our own galaxy. Astronomers catalogued it, gave it a number and moved on. Messier 31. A nebula, unremarkable, close, ours. Then in 1925, a man named Edwin Hubble pointed a telescope at that smudge and measured something that should not have been possible. It wasn't close, it wasn't ours. It was 2.5 million light-years away. An entire galaxy, a separate island of stars so vast it contained 1 trillion suns, and in one observation, the universe we thought we lived in evaporated. But here's the part no one talks about in the history books. That galaxy, the one we now call Andromeda, isn't just sitting out there in the dark. It's moving toward us at 250,000 miles per hour. And it has been moving toward us since long before humans existed. Right now, as you sit here, Andromeda is 5 million light-years away and closing. In 4.5 billion years it will arrive, not as a visitor, as a collision. 1 trillion stars crashing into our own galaxy in the longest, slowest, most inevitable merger the local universe will ever see. The Milky Way as we know it will cease to exist. Andromeda will cease to exist. And in their place, something new will be born. Scientists have a name for it already: Milkomeda. So what happens when two galaxies collide? What happens to Earth, to the Sun, to the night sky our distant descendants might still be looking up at when the first stars from Andromeda begin tearing through our spiral arms? And why, in a universe that's supposed to be expanding, are we on a collision course at all? This is that story. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. There is a smudge in the sky. It sits in the constellation Andromeda, roughly halfway between the bright star Alpheratz and the great square of Pegasus. On a clear autumn night, far from city lights, you can see it with your naked eye, a faint blur, a soft patch of grayish light shaped like a stretched cigar lying on its side. Nothing dramatic, nothing that demands attention, just a quiet presence in the dark. For most of human history, that smudge was nameless. Ancient Persian astronomers noted it in the 10th century. They called it the Little Cloud. Medieval stargazers in Europe and the Middle East saw it too, catalogued it as a curiosity, and moved on. It did not change, it did not flare. It simply hung there, exactly where it had always been, waiting for someone to ask the right question. That question took a very long time to arrive. In 1612, a German astronomer named Simon Marius pointed a telescope at the smudge. He was among the first generation of scientists to peer through lenses at the heavens, and what he saw puzzled him. The blur resolved slightly under magnification, but not into individual stars. It remained a soft glow, brighter in the center, fading at the edges. Marius described it as resembling the light of a candle seen through a sheet of horn. Poetic, but not particularly useful. He had no framework to explain what he was looking at. No one did. Telescopes in that era were crude instruments, barely more sophisticated than a spyglass you might use to watch ships at sea. They magnified, yes, but they distorted. They smeared light. They turned sharp points into halos and clear objects into fog. The smudge in Andromeda, already faint, became even harder to interpret when filtered through 17th century optics. So astronomers did what scientists always do when confronted with something they cannot explain. They gave it a name and filed it away for later. In 1764, the French astronomer Charles Messier was hunting for comets. Comets were the celebrity objects of the era, bright visitors that swept through the inner solar system, trailing tails of gas and dust. They moved, they changed, they were news. Messier wanted to find them before anyone else did, which meant scanning the sky night after night with a telescope, looking for anything fuzzy that might be a new arrival. The problem was that the sky is full of fuzzy things that are not comets, nebulae, star clusters, distant clouds of gas glowing faintly in the dark. Every time Messier spotted one, he wasted hours confirming that it was not moving, that it was not what he was looking for. Eventually, he got tired of being fooled and decided to make a list, a catalogue of permanent fuzzy objects that future astronomers could cross-reference so they would not waste their time the way he had. The smudge in Andromeda became the 31st entry on that list, Messier 31, M31 for short. And for more than a century, that is all it was, a catalogued nuisance, a thing that looked like a comet but was not. By the late 1700s, telescopes had improved. William Herschel, a musician turned astronomer working in England, built some of the largest and most powerful reflecting telescopes of his time. He mapped the heavens with obsessive precision, sweeping across constellations night after night, counting stars, measuring positions, trying to map the shape of the Milky Way itself. When Herschel looked at M31, he saw structure, faint wisps extending outward from the central glow. He called it Lord Ross's object, after another astronomer who had sketched similar features. Herschel estimated its apparent size at roughly 4 arc-minutes across, about 1/8 the diameter of the full moon. He assumed it was a cloud of gas somewhere inside the Milky Way, perhaps a region where new stars were forming. The assumption was reasonable given the tools available. There was no reason to think otherwise. The Milky Way was the universe. Everything visible in the sky was part of it. Distant stars, glowing clouds, clusters of light, all of it lived inside a single cosmic structure with Earth somewhere near the middle. That was the picture astronomers carried into the 20th century. A universe contained, mapped, understood. Then the argument started. By 1920, astronomers had amassed enough data on nebulae to realize they did not all fit into neat categories. Some were clearly clouds of gas and dust glowing because of nearby stars. Others, called spiral nebulae because of their coiled shapes, were harder to explain. They did not look like gas clouds. They looked organized, structured, almost mechanical in their geometry, and they were moving. Measurements of their light revealed that most spiral nebulae were receding from Earth at enormous speeds. Some astronomers, led by Harlow Shapley of the Mount Wilson Observatory, argued that these spiral nebulae were relatively nearby objects, perhaps 20,000 light-years away, sitting well within the boundaries of the Milky Way. Shapley had recently completed a groundbreaking study of globular clusters, dense spheres of old stars orbiting the galactic core, and his work had pushed the known size of the Milky Way outward dramatically. He was not eager to expand the universe again so soon. If the spiral nebulae were extragalactic, sitting millions of light-years away, it would mean the cosmos was orders of magnitude larger than anyone had imagined. Shapley found that uncomfortable. Heber Curtis, an astronomer at Lick Observatory in California, disagreed. Curtis believed the spiral nebulae were island universes, separate galaxies comparable in size and structure to the Milky Way itself. He pointed to the enormous velocities measured in their spectra. If these objects were nearby, he argued, they would be moving faster than any known object in the galaxy, which made no sense. He also noted that several novae, exploding stars, had been observed in spiral nebulae. If the nebulae were distant galaxies, those novae would have to be extraordinarily bright to be visible from Earth, but the math worked. If they were nearby clouds within the Milky Way, the novae would be impossibly luminous, brighter than anything else in the known universe. Curtis thought the island universe theory fit the data better. Shapley thought Curtis was overreaching. In April 1920, the two men faced off in Washington, D.C. at the headquarters of the United States National Academy of Sciences. The event was billed as a debate, though in practice it was more of a polite exchange of lectures. Shapley presented his case for a large but singular Milky Way. Curtis laid out his argument for a universe full of separate galaxies. Neither man convinced the other. The audience, made up largely of scientists who specialized in other fields, left without a clear sense of who had won. The data was too ambiguous. The instruments were not yet precise enough to settle the question cleanly. The great debate, as it came to be known, ended in a draw, and the smudge in Andromeda remained a mystery. 3 years later, Edwin Hubble aimed the 100-inch Hooker telescope at Mount Wilson directly at M31. The Hooker was at the time the largest and most powerful telescope on Earth, a massive reflecting instrument perched in the mountains above Los Angeles. Hubble was methodical, patient, and unusually skilled at photographic observation. He took long exposure images of the outer regions of the Andromeda Nebula, areas where individual points of light could be resolved against the background glow. He was looking for Cepheid variables, a specific type of star that brightens and dims on a regular cycle. Cepheids had been studied extensively by Henrietta Leavitt, an astronomer at Harvard College Observatory, who in 1912 discovered a direct relationship between the period of a Cepheid's pulsation and its intrinsic luminosity. A Cepheid that pulsed slowly was intrinsically brighter than one that pulsed quickly. If you could measure how long it took a Cepheid to complete one cycle, you could calculate how bright it actually was. Compare that true brightness to how bright it appeared from Earth, and you had a distance, a cosmic yardstick. Hubble found his Cepheids. He tracked them over weeks and months, recording their brightening and dimming, measuring their periods. The math that followed was straightforward, but the result was staggering. The Cepheids in Andromeda had periods consistent with very high intrinsic luminosities, but they appeared faint from Earth, extraordinarily faint. The only way to reconcile those two facts was to place Andromeda at an enormous distance. Hubble calculated roughly 900,000 parsecs. That translates to about 2.5 million light-years. Andromeda was not inside the Milky Way. It was not 20,000 light-years away. It was not even close. It was a separate galaxy, an island universe, exactly as Curtis had predicted. And it was huge, comparable in size to the Milky Way itself, possibly larger. Hubble announced his findings in 1925. The response from the astronomical community was immediate and seismic. The universe had just become incomprehensibly larger. The Milky Way was no longer the cosmos. It was one galaxy among many. The smudge in Andromeda, visible to the naked eye since before recorded history, was not a cloud or a cluster. It was an entire galaxy, a structure containing hundreds of billions of stars, sitting so far away that its light took 2.5 million years to reach Earth. When you looked at that faint blur on a clear autumn night, you were seeing Andromeda as it existed when the earliest human ancestors were just beginning to walk upright on the plains of Africa. The light crossing that distance was older than our species. Shapley conceded almost immediately. He had been wrong. The data was clear. Curtis had been right about the island universes. The cosmos was not contained. It extended outward in every direction, filled with galaxies beyond counting. Astronomers began finding them everywhere, thousands in deep exposures, tens of thousands, millions. The scale of the known universe expanded by a factor of 10 overnight and then kept expanding. Every assumption about our place in the cosmos had to be rewritten. Earth was not the center of the solar system. The sun was not the center of the galaxy. And the galaxy itself was not the center of anything. It was a single point of light in an ocean of galaxies stretching billions of light years in every direction. That shift, that moment when the smudge in Andromeda revealed itself as something far stranger and far grander than a cloud of gas, is one of the most profound reorientations in the history of human thought. It ranks alongside the realization that the Earth orbits the Sun, that the continents drift, that life evolves. It changed not just what we knew, but how we understood knowing. The universe was no longer something we could map from a single vantage point. It was something we had to explore, piece by piece, with instruments that could see farther than human eyes were ever designed to reach. And the irony is that Andromeda had been sitting there the whole time, visible, catalogued, studied, a faint smudge that anyone with decent eyesight could find on a dark night. It took telescopes, mathematics, and the patience of astronomers like Leavitt and Hubble to decode what that smudge actually was, to realize that the light reaching our eyes had traveled across voids so vast that the human mind struggles to hold them, to understand that we live in a universe populated by structures so large that our entire solar system would be invisible if viewed from Andromeda's core. The smudge had always been a galaxy. We just were not ready to see it yet. That readiness came at a cost. Once you accept that Andromeda is a galaxy, you have to accept everything that follows. You have to accept that the universe is not static, that it is expanding, that galaxies are moving apart from one another at speeds that defy everyday intuition. You have to accept that the light we see from distant galaxies left those galaxies billions of years ago, that we are looking backward through time every time we point a telescope at the sky, and you have to accept that Andromeda, sitting just 2.5 million light-years away, is not just a distant object to be admired. It is a neighbor, and it is moving, not away, toward, straight at us, at roughly 110 kilometers per second, and it has been closing that distance for billions of years. That realization, which came decades after Hubble's breakthrough, changed Andromeda from a historical curiosity into something far more unsettling, a reminder that the universe is not a museum, it is a machine, and we are inside it. Unveiling the cosmic colossus, Andromeda's grandeur. Once you accept that the smudge in Andromeda is a galaxy, the next question arrives immediately. How big is it? Not in angular size, not in how much sky it covers from our perspective, but in actual physical dimensions. How much space does this thing occupy? How many stars does it contain? How much mass is packed into its structure? And most importantly, how does it compare to our own galaxy, the Milky Way, the cosmic neighborhood we've spent centuries trying to map from the inside? The answers to those questions took decades to pin down. Hubble's discovery in 1925 told us Andromeda was distant and separate. It did not tell us how large it was. Measuring the size of a galaxy sitting 2.5 million light-years away is not as simple as stretching a tape measure across the sky. You need to map its edges, identify where the stars thin out, where the light fades into the background darkness of intergalactic space. You need to account for dust that blocks your view, for stars too faint to see, for the diffuse glow of gas and dark matter that extends far beyond the visible disk. And you need to do all of that using instruments that, for most of the 20th century, were barely capable of resolving individual stars at Andromeda's distance. By the 1950s, astronomers had a rough estimate. Andromeda appeared to be larger than the Milky Way, perhaps significantly so. Photographic plates taken with the largest telescopes of the era showed a broad oval disk tilted at an angle, with spiral arms curling outward from a dense, bright core. The visible structure stretched across roughly 3 degrees of sky, about 6 times the apparent diameter of the full moon. Multiply that angular size by the known distance, and you get a diameter of somewhere around 150,000 light-years. Bigger than the Milky Way's estimated 100,000 light-year span, but not absurdly so. A sibling galaxy, slightly larger, sitting comfortably within the range of what theory predicted large spiral galaxies should look like. Then better instruments came online. Deep sky surveys in the 1980s and 1990s using charge-coupled device cameras, which are far more sensitive than photographic film, revealed that Andromeda's outer regions extended much farther than anyone had realized. Faint streams of stars, barely visible against the background sky, traced loops and arcs stretching well beyond the main disk. These were not random stragglers. They were structured, organized into shells and tidal tails, the remnants of smaller galaxies that Andromeda had consumed over billions of years. Follow those streams outward, and Andromeda's effective diameter grows. 150,000 light-years becomes 200,000, then 220,000. By the early 2000s, observations from the Hubble Space Telescope and ground-based surveys like the Sloan Digital Sky Survey pushed the number even higher. 260,000 light-years from edge to edge, measured along the outermost detectable streams of stars. That makes Andromeda the largest galaxy in the local group by a significant margin. The local group is the name astronomers give to the collection of galaxies bound together by gravity in our immediate cosmic neighborhood. It contains about 50 known members, most of them small dwarf galaxies with a few billion stars each. The Milky Way and Andromeda are the two dominant structures, the gravitational anchors around which everything else orbits. The third largest member, a spiral galaxy called Triangulum, or M33, sits at roughly 60,000 light-years across, respectably sized but dwarfed by Andromeda. If you lined up the Milky Way and Andromeda side by side, Andromeda would be more than twice as wide. Not a small difference, a dramatic one. But size is only part of the story. Mass is what matters in the universe. Gravity does not care how much space an object occupies. It cares how much matter is packed into that space. And this is where things get complicated, because Andromeda's mass has been one of the most contested numbers in galactic astronomy for the better part of 4 decades. Early estimates based on the rotation speeds of stars in Andromeda's outer disk suggested a total mass of around 1.5 trillion solar masses. That number includes everything: stars, gas, dust, and the enormous halo of dark matter that surrounds the visible galaxy. Dark matter, which we cannot see directly but can infer from its gravitational effects, makes up the vast majority of any galaxy's mass. In a typical large spiral galaxy, stars and gas account for maybe 10 to 20% of the total. The rest is dark matter, a mysterious substance that does not emit light, does not absorb light, does not interact with electromagnetic radiation in any way we can currently detect. It just pulls. And it pulls hard enough to hold galaxies together, to keep stars in the outer regions moving faster than they should if only visible matter were present. If Andromeda weighs 1.5 trillion solar masses, it would be the most massive galaxy in the local group by a comfortable margin. Our Milky Way, by comparison, was long estimated at somewhere between 700 billion and 1 trillion solar masses, depending on how you measured it. Andromeda wins, case closed, except the case did not stay closed. In 2009, a team of astronomers published a revised mass estimate for the Milky Way. Using data from the Sloan Digital Sky Survey and new models of the galaxy's dark matter halo, they concluded that the Milky Way might weigh significantly more than previously thought, possibly as much as 1.5 trillion solar masses, the same as Andromeda, or close enough that the difference fell within the margin of error. That result surprised a lot of people. The Milky Way is smaller in diameter. It contains fewer stars. How could it possibly match Andromeda in total mass? The answer is dark matter. Again, the Milky Way's dark matter halo appears to be unusually dense and unusually extended. It may reach farther out into intergalactic space than Andromeda's does, pulling in more total mass, even though the visible galaxy is more compact. Some models suggest the Milky Way's halo could extend as far as 600,000 light-years from the galactic center, well beyond the orbit of the Magellanic Clouds, the two dwarf galaxies currently spiraling inward toward us. If that is correct, then the Milky Way is not Andromeda's smaller sibling. It is Andromeda's rough equal, a heavyweight in its own right, just built along different lines. More recent studies have added another twist. In 2018, a team analyzing Gaia satellite data, which tracks the positions and motions of more than 1 billion stars in the Milky Way with extraordinary precision, published a new mass estimate. They concluded that the Milky Way weighs roughly 800 billion solar masses, lower than the 2009 estimate, but still respectably massive. They also ran the same analysis on Andromeda using Hubble data and came up with a similar number, 800 billion solar masses, not 1.5 trillion. Suddenly, both galaxies are lighter than we thought, and they are almost perfectly matched. The truth is, we do not know exactly how much either galaxy weighs. The measurements are hard. Dark matter does not cooperate. It does not glow. It does not cluster neatly. It forms an invisible scaffolding that holds galaxies together, and the only way to weigh it is to watch how visible matter moves under its influence. Stars orbiting the galactic core, gas clouds drifting through the outer halo, satellite galaxies falling inward over millions of years. Each method gives a slightly different answer, and the uncertainties are large enough that picking a winner between the Milky Way and Andromeda is not straightforward. What we can say with confidence is that they are comparable, same weight class, same scale, two spiral galaxies sitting at the center of the local group, each massive enough to dominate everything around them. Now let's talk about stars, because Andromeda has a lot of them, roughly 1 trillion, give or take a few hundred billion, depending on whose count you trust. Compare that to the Milky Way's 200 to 400 billion stars, and Andromeda is clearly the more populous galaxy. It has more than twice as many stars, possibly 3 times as many. That discrepancy is why Andromeda is visibly larger, even though the total mass is similar. The stars are more spread out, distributed across a wider disk, with a thicker bulge and more extensive spiral arms. The Milky Way packs its stars more tightly, which makes it more compact, but also denser in the inner regions. Andromeda's structure is classic spiral. 2 main arms curl outward from the central bulge, tracing smooth arcs through the galactic disk. The arms are rich in blue light, a sign of young hot stars and active star formation. Gas clouds collapse, stars ignite, and the brightest among them, massive blue giants that burn through their fuel in just a few million years, light up the arms like streetlights along a highway. Between the arms, the disk is dimmer, populated by older, redder stars that have been orbiting quietly for billions of years. The bulge at the center glows with a warmer yellowish light, dominated by ancient stars formed when the galaxy was young. This is not unusual. Most spiral galaxies follow the same basic pattern. What makes Andromeda interesting is the details. Deep imaging has revealed that the galaxy is not quite as symmetrical as it looks at first glance. One of the spiral arms is more prominent than the other. The disk shows signs of warping, bending slightly out of the main plane in the outer regions, and there is a peculiar ring of dust sitting about 30,000 light-years from the core, tilted at an odd angle relative to the rest of the galaxy. That ring is almost certainly the result of a past collision. A smaller galaxy that wandered too close, got torn apart by tidal forces, and left behind a scar in Andromeda's structure. The most likely culprit is M32, a compact elliptical galaxy currently sitting very close to Andromeda's core, practically embedded in the larger galaxy's outer disk. M32 is small, only about 6,000 light-years across, but it is dense, packed with stars in a tight spherical ball. Computer simulations suggest that M32 may have once been much larger, a normal spiral galaxy that plunged through Andromeda's disk hundreds of millions of years ago. The collision stripped away M32's outer layers, scattering stars and gas into Andromeda's structure, and left behind only the dense core we see today. That stolen material now orbits as part of Andromeda, mixed into the disk, indistinguishable from the stars that have always been there. Galactic cannibalism is not a rare event. It is how large galaxies grow. Andromeda has been eating its neighbors for billions of years. The faint stellar streams visible in deep images, those loops and arcs extending far beyond the main disk, are the digested remains of at least a dozen smaller galaxies. Each one fell inward, torn apart by tidal forces, stretched into long filaments of stars that now orbit Andromeda like ghosts. Some of those streams are still coherent enough to trace back to their source. Others have been scrambled by repeated orbits, mixed into the halo until their original identity is lost. This is how galaxies build mass over time, not by forming new stars out of the void, but by accreting smaller systems, swallowing them whole, and incorporating their matter into the larger structure. The Milky Way is doing the same thing. Right now, we are in the process of consuming the Sagittarius dwarf elliptical galaxy, a small system that has been orbiting through our disk for billions of years, shedding stars with each pass. Eventually, nothing will be left but a stream of debris wrapped around the Milky Way's core. That process is slow, measured in hundreds of millions of years, but it is relentless. And Andromeda, being larger and more massive, has been even more aggressive about it. The stellar populations inside Andromeda tell a history written in light. The central bulge is old. The stars there formed more than 10 billion years ago, back when the universe was less than a quarter of its current age. They are metal-rich, meaning they contain heavier elements forged in earlier generations of stars, a sign that the bulge assembled quickly in the early universe from gas that had already been processed through multiple cycles of stellar birth and death. The disk is younger on average, with stars spanning a wide range of ages from ancient to newborn. The spiral arms are where the action is happening now. Massive clouds of hydrogen gas collapse under their own gravity, fragment into clumps, and ignite as new stars. The brightest of those stars, blue supergiants weighing tens of times the mass of our Sun, live fast and die young, exploding as supernovae within a few million years. Their deaths seed the surrounding gas with heavy elements, enriching the next generation of stars, and the cycle continues. Star formation in Andromeda is not as vigorous as it once was. Observations in the infrared, which can peer through dust to see where new stars are being born, suggest that Andromeda forms roughly one new solar mass of stars per year. That sounds like a lot until you compare it to the total stellar population. 1 trillion stars formed over 10 billion years averages out to about 100 solar masses per year in the past. The rate has slowed. Andromeda is not dead, but it is cooling down, transitioning from an active star-forming galaxy to a more sedate middle-aged system. The Milky Way is doing something similar, forming new stars at a rate of about 2 solar masses per year, also down from its peak billions of years ago. The halo surrounding Andromeda is where the oldest and most metal-poor stars live. These are relics from the galaxy's earliest days, formed before the disk and bulge had fully assembled. They orbit in a vast spherical cloud, extending hundreds of thousands of light-years from the center, moving on highly elliptical paths that take them far out into intergalactic space before swinging back inward. The halo also contains roughly 450 globular clusters, dense spheres of ancient stars that formed very early in the universe's history. Each cluster contains anywhere from tens of thousands to a few million stars packed into a region only a few dozen light-years across. They are some of the oldest objects in the galaxy, fossils from the epoch of galaxy formation, and studying them gives astronomers a window into what the early universe looked like. The Milky Way has about 150 known globular clusters. Andromeda has 3 times as many. That difference reflects Andromeda's larger size and more violent merger history. Every time Andromeda swallowed a smaller galaxy, it inherited that galaxy's globular clusters, adding them to its own collection. Some of those clusters are now scattered throughout the halo, following orbits that trace back to long-dead galaxies. Others are still loosely grouped, remnants of their original host system that have not yet been fully dispersed. Andromeda also has a companion galaxy worth mentioning, M110, a dwarf elliptical sitting about 200,000 light-years from Andromeda's core, visible in the same telescopic field of view. M110 contains roughly 10 billion stars, making it one of the more substantial members of Andromeda's satellite system. It shows signs of recent star formation, which is unusual for a dwarf elliptical. Most elliptical galaxies, regardless of size, are considered dead, their gas exhausted, their star formation shut down billions of years ago. M110 has pockets of young blue stars scattered through its central regions, a hint that it may have experienced a recent interaction, possibly a close pass with Andromeda or another satellite that compressed its gas and triggered a burst of new stellar birth. Then there is the question of whether M33, the Triangulum galaxy, is truly a satellite of Andromeda or an independent member of the local group. M33 sits about 250,000 light-years from Andromeda, close enough that gravitational interactions are likely. Some models suggest M33 is on a long elliptical orbit around Andromeda, possibly making its first close approach. Others argue the motion is too uncertain, the distance too large, and M33 should be treated as a separate object, not bound to either Andromeda or the Milky Way. The data does not yet settle the question cleanly. What is clear is that Andromeda has accumulated at least 14 confirmed dwarf satellite galaxies, small systems bound by gravity to orbit the larger galaxy like moons around a planet. The Milky Way has a similar collection. Both galaxies are the gravitational centers of their own small empires, surrounded by smaller systems, slowly spiraling inward. Which brings us to dark matter. Again, because no discussion of Andromeda's grandeur is complete without acknowledging that most of the galaxy is invisible. The 1 trillion stars, the gas clouds, the dust, the globular clusters, all of it, every piece of matter we can observe, accounts for maybe 15 to 20% of Andromeda's total mass. The rest is dark matter, spread out in a massive halo that extends far beyond the visible edge of the galaxy. That halo is what binds Andromeda together. Without it, the outer stars would be moving too fast to stay in orbit. They would fly off into intergalactic space, unraveling the galaxy over time. The fact that they do not, that Andromeda has remained intact for billions of years despite the high velocities of its stars, tells us the dark matter is there, holding everything in place with its gravity. We do not know what dark matter is. Decades of experiments have failed to detect it directly. It does not emit light, it does not absorb light, it does not interact with ordinary matter except through gravity. Every attempt to capture a dark matter particle in a laboratory detector has come up empty. Yet we know it exists because we can see its effects. We can measure the rotation curves of galaxies, watch how fast stars move at different distances from the center, and calculate how much mass is required to produce those speeds. The answer is always more than the visible matter can provide, sometimes much more. In Andromeda's case, the dark matter halo likely extends 500,000 light-years or more from the galactic core, a vast, invisible structure that dwarfs the visible galaxy. That halo is not static. It is constantly shifting, responding to the gravitational pull of nearby galaxies, particularly the Milky Way. Computer simulations of the local group show that Andromeda and the Milky Way are locked in a slow gravitational dance, their dark matter halos overlapping at the edges, pulling on each other across the 2.5 million light-years of space between them. That pull is what is driving the two galaxies together, accelerating them toward an eventual collision. And the mass of those halos, the sheer amount of dark matter packed into the space around each galaxy, is what will determine the violence of that collision, the speed of the impact, and the shape of the merged galaxy that results. Andromeda is a monster, not because it is hostile, not because it poses any immediate threat, but because of its scale. A structure containing 1 trillion stars, bound by invisible matter, stretching across hundreds of thousands of light-years, surrounded by the remnants of galaxies it has consumed over billions of years. It is a colossus, a cosmic giant, and it is heading toward us at 110 kilometers per second. Every second, Andromeda closes the distance by 110 kilometers. Every hour, that gap shrinks by 400,000 kilometers. Every day, nearly 10 million kilometers. Every year, 3.5 billion kilometers. And it has been doing this for billions of years. The distance between us and Andromeda has been shrinking since long before Earth existed, and it will continue shrinking until the two galaxies meet. But before we talk about the collision, before we walk through what happens when two massive spirals slam into each other at relativistic fractions of the speed of light, we need to understand what is sitting at Andromeda's core. Because every large galaxy has a heart, a central engine that drives its evolution, and Andromeda's heart is one of the strangest objects in the local group. The engine of collapse, Andromeda's supermassive heart. Before we can understand what happens when two galaxies collide, we need to talk about the thing sitting at the center of almost every large galaxy in the universe, a supermassive black hole. Not the small stellar mass kind that forms when a massive star collapses at the end of its life, weighing maybe 10 or 20 times the mass of our Sun. The other kind, the kind that weighs millions or billions of solar masses, the kind that sits at the galactic core like a spider in the center of a web, holding everything around it in a gravitational grip so tight that nothing within a certain radius can ever escape. For most of the 20th century, astronomers did not believe these objects existed. Black holes were theoretical curiosities, solutions to Einstein's equations that seemed too strange to be real. Even after stellar mass black holes were tentatively identified in the 1970s through observations of binary star systems where one companion was invisible but clearly pulling on the other, the idea of a black hole weighing 1 million times more than the Sun seemed absurd. Where would it come from? How would it form? What would prevent it from swallowing the entire galaxy? Then the data started piling up. Observations of the centers of nearby galaxies revealed something odd. Stars near the cores were moving too fast. Gas clouds were orbiting at velocities that required an enormous concentrated mass to explain. And some galaxies, particularly a class called active galactic nuclei, were emitting truly staggering amounts of energy from regions smaller than our solar system. The only explanation that fit the data was a supermassive black hole, millions or billions of times the mass of the Sun, sitting at the galactic center, pulling in gas and stars, heating that material to millions of degrees as it spiraled inward, and producing jets of radiation visible across the universe. By the late 1990s, the evidence was overwhelming. Nearly every large galaxy observed in detail showed signs of a central supermassive black hole. The Milky Way had one. Andromeda had one. Every spiral, every elliptical, every massive galaxy we could measure closely enough to map the motions of stars near the core, all of them had black holes. Not anomalies, not rare exceptions, standard equipment. If you are a galaxy with more than a few tens of billions of stars, you have a supermassive black hole at your center. That is the rule. Our own galaxy's black hole is called Sagittarius A star, named after the constellation where it sits in our sky. Sagittarius A star weighs about 4 million solar masses. That sounds enormous until you realize it represents only about 0.1% of the Milky Way's total stellar mass. The black hole is not the galaxy. It is a tiny fraction of the galaxy's mass, sitting at the very center, influencing only the innermost regions where stars are packed densely enough to feel its pull. Most stars in the Milky Way, including our Sun, orbit the galactic center without ever coming close to the black hole. The Sun is sitting about 26,000 light-years from Sagittarius A star, far enough that the black hole's gravity is negligible compared to the combined pull of all the stars and dark matter distributed throughout the galaxy. But get close to the core, within a few light-years, and Sagittarius A star dominates. Stars there are whipping around at thousands of kilometers per second, completing orbits in just a few years. We have tracked some of those stars for decades now, watching them loop around an invisible point, accelerating as they approach, slowing as they recede, following perfect elliptical paths dictated by a central mass that emits no light. One star, designated S2, completes a full orbit in just 16 years. At its closest approach, it passes within about 17 light-hours of the black hole, moving at nearly 5% the speed of light. That is fast enough that relativistic effects become measurable. The star's light gets redshifted as it climbs out of the black hole's gravitational well, exactly as Einstein's theory predicts. Observing those stars, mapping their orbits, and calculating the mass required to produce those trajectories is how astronomers confirmed that Sagittarius A star exists and measured its weight. 4 million solar masses packed into a region smaller than the orbit of Mercury. That is a supermassive black hole, and compared to what sits at the center of Andromeda, it is a lightweight. Andromeda's black hole weighs roughly 100 million solar masses. Some estimates push it as high as 140 million. Either way, it is about 25 times more massive than Sagittarius A star. 25 times. That difference matters because the size of a black hole's event horizon, the boundary beyond which nothing can escape, scales directly with its mass. Sagittarius A star has an event horizon with a radius of about 12 million kilometers. Andromeda's black hole has a radius closer to 300 million kilometers. That is roughly twice the distance from the Earth to the Sun. The event horizon alone, just the point of no return, spans a distance that would swallow the inner solar system. For a long time, astronomers knew Andromeda had to have a supermassive black hole. The galaxy was too large, too massive, too well organized not to have one. But actually finding it, measuring it, and confirming its properties took decades of work. The problem is that black holes do not emit light. You cannot point a telescope at one and take a picture. You have to infer its presence by watching how matter behaves nearby. And Andromeda's core is crowded, packed with millions of stars, clouds of gas and dust, and a strange double nucleus structure that confused observers for years. That double nucleus is one of Andromeda's most peculiar features. Look at the galaxy's center with a powerful telescope, and instead of seeing a single bright point like you would expect at the heart of a spiral galaxy, you see two distinct concentrations of light sitting very close together, separated by only about 5 light-years. For decades, astronomers debated what they were looking at. Were there two black holes? Was this the result of a recent merger, two galactic cores that had not yet fully combined? Or was something else going on, something stranger that did not fit the standard picture of how galaxy centers should look? The answer came in 2005, when a team of astronomers used the Hubble Space Telescope to take spectroscopic measurements of the stars near Andromeda's core. Spectroscopy breaks light into its component wavelengths, revealing not just how bright an object is, but how fast it is moving. Stars moving toward us show up slightly blue-shifted, their light compressed to shorter wavelengths. Stars moving away show up red-shifted, their light stretched. Measure the motion of stars throughout a region, and you can map the gravitational field, identify where the mass is concentrated, and figure out what is pulling on what. The Hubble data revealed that one of the two bright nuclei was not a nucleus at all. It was a dense cluster of old blue stars packed tightly together, but not sitting at the gravitational center. The actual center, the point where the black hole resides, was the other nucleus, designated P3. P3 is not particularly bright compared to the surrounding stars, which is why it took so long to identify. But it sits exactly where the gravitational center should be, and the motions of nearby stars confirm that an enormous mass is concentrated there. 100 million solar masses packed into a region too small to resolve with any existing telescope. A black hole. The star cluster, the false nucleus, sits about 5 parsecs away from P3, which translates to roughly 16 light-years. That cluster contains millions of stars, all old, all blue, all orbiting the true center in a tight elliptical path. The cluster is not falling into the black hole, not yet, but it is bound to P3 gravitationally, trapped in an orbit that has persisted for millions of years. Why the cluster exists, why it formed so close to the black hole, and why it has survived without being torn apart, are questions astronomers are still working on. The leading theory is that the cluster formed from gas that was funneled toward the galactic center during a past merger, possibly the same event that brought in the material now forming the tilted dust ring visible in Andromeda's inner disk. P3 is not actively feeding, at least not in the dramatic way that powers quasars and active galactic nuclei. There is no massive accretion disk glowing at millions of degrees. There are no jets of radiation shooting out from the poles. P3 is quiet, dormant, sipping gas at a relatively slow rate. Most supermassive black holes spend the majority of their lives in this state, quiescent, surrounded by a sparse halo of gas and stars, but not actively consuming large amounts of material. The violent feeding phases, the ones that light up a galaxy's core and make it visible across the universe, only happen when something disrupts the system and sends a large amount of gas or stars plunging inward. A galaxy merger, a close pass with another galaxy, or the tidal disruption of a star that wandered too close and got shredded by the black hole's gravity. Andromeda has experienced plenty of mergers in its past. The stellar streams visible in deep images, the remnants of consumed dwarf galaxies, the tilted dust ring, the star cluster near P3, all of it points to a violent history. Each time Andromeda swallowed a smaller galaxy, some of that galaxy's gas and stars were funneled toward the core, feeding P3, causing it to grow. That growth was not continuous. It happened in bursts, episodes of rapid accretion separated by long, quiet periods. Right now, we are in one of those quiet periods. P3 is not glowing. It is not producing jets. It is just sitting there, exerting its gravitational pull, shaping the orbits of the stars and gas around it, waiting for the next meal to arrive. And the next meal is coming. In about 4.5 billion years, when Andromeda and the Milky Way collide, the two supermassive black holes at their centers will be driven toward each other by the dynamics of the merger. That process will take hundreds of millions of years. The galaxies will pass through each other multiple times, their structures distorted by tidal forces, stars and gas flung outward in long streamers. With each pass, the two black holes will sink deeper into the merged system, losing energy to gravitational interactions with surrounding stars. Eventually, they will find each other. Two black holes, one weighing 100 million solar masses, the other weighing 4 million, spiraling inward, their orbits decaying, the distance between them shrinking from light years to light months to light days. When they finally merge, the event will release an enormous pulse of gravitational waves, ripples in the fabric of space-time that will propagate outward at the speed of light. Observatories on Earth, assuming humanity is still around and still operating gravitational wave detectors, will pick up that signal. It will be one of the loudest events ever recorded, a collision between two objects so massive that their merger will shake the structure of space itself. The resulting black hole will weigh roughly 104 million solar masses, slightly less than the sum of the two original black holes, because a few million solar masses worth of energy will be radiated away as gravitational waves during the final moments of the inspiral. That merged black hole will sit at the center of the new galaxy, which astronomers have already named Milkomeda. It will be the gravitational anchor for the entire system, surrounded by a dense core of stars, most of them old and red, scattered inward during the chaotic interactions of the merger. Over billions of years, stars will continue to fall toward the center, feeding the black hole in a slow, steady trickle. Some will be torn apart by tidal forces before they reach the event horizon, their gas stripped away and heated to millions of degrees, glowing brightly for a few weeks or months before being swallowed. Others will pass the horizon intact, adding their mass to the black hole without any visible sign that anything happened. But that is billions of years away. Right now, P3 sits quietly at Andromeda's core, invisible to our telescopes, detectable only through the motions of the stars around it. It is not a threat. It is not reaching across space trying to pull the Milky Way inward. Black holes do not do that. They do not suck. They pull the same way any massive object pulls, following the same rules of gravity that govern planets, stars, and galaxies. The only difference is that if you get too close to a black hole, closer than the event horizon, the pull becomes so strong that not even light can climb back out. Stay outside that boundary, and a black hole is no more dangerous than any other object of the same mass. You could orbit a black hole the same way Earth orbits the Sun, as long as you kept your distance. The influence P3 has on Andromeda extends far beyond the event horizon. The black hole's gravity shapes the orbits of stars within the inner few hundred light-years of the galactic core. It heats gas through friction as that gas spirals inward, preventing some of it from collapsing to form new stars. It creates a region of intense gravitational shear where stars on slightly different orbits experience different amounts of pull, stretching and distorting their paths over time, and it serves as the anchor point around which the entire galaxy rotates. Every star in Andromeda, from the outermost halo to the densest regions of the bulge, is ultimately orbiting P3 and the surrounding mass distribution. The black hole is not the only thing pulling, but it is the center, the fixed point, the heart of the system. The fact that nearly every large galaxy has one of these objects tells us something important about how galaxies form and evolve. Supermassive black holes are not afterthoughts. They are not accidents. They are integral to the structure of galaxies, possibly even necessary for galaxies to grow as large as they do. The correlation between a galaxy's mass and the mass of its central black hole is remarkably tight. Bigger galaxies have bigger black holes, almost without exception. The relationship is not perfect, but it is strong enough that astronomers can estimate a galaxy's black hole mass just by measuring the galaxy's total stellar mass, or the speed at which stars in the bulge are moving. That correlation suggests the black hole and the galaxy grow together, feeding off the same reservoir of gas, influencing each other's evolution. When a galaxy merges with another galaxy, both black holes sink toward the center of the merged system and eventually combine, creating a larger black hole. When gas flows inward during a starburst event, some of it feeds the black hole, causing it to grow while the rest forms new stars. The black hole can also regulate star formation by heating gas to temperatures too high for it to collapse, creating a kind of feedback loop that limits how large the galaxy can become. Too much star formation funnels too much gas to the black hole. The black hole heats the surrounding region and star formation shuts down. The galaxy stabilizes at a size determined by the balance between inflow, star formation, and black hole feedback. Andromeda's black hole is unusually massive for a galaxy of its size. Most galaxies with Andromeda's stellar mass have black holes weighing somewhere between 30 and 50 million solar masses. P3 is 2 or 3 times heavier than that. The reason is probably Andromeda's merger history. Every time Andromeda consumed a smaller galaxy, it inherited that galaxy's black hole. Those smaller black holes sank toward the center and merged with P3, adding their mass to the total. Andromeda has eaten a lot of galaxies over the past 10 billion years, and P3 is the accumulated result of all those meals. A black hole built from dozens of smaller black holes, each one dragged inward by the dynamics of a merger, each one contributing a few million or a few tens of millions of solar masses to the growing monster at the core. The discovery of P3 in 2005 was not just about identifying Andromeda's black hole. They are engines, the unseen mechanisms that drive galactic evolution, regulate star formation, and shape the distribution of matter on the largest scales. P3 is one of those engines, and in a few billion years it will combine with Sagittarius A star to produce an even larger engine, sitting at the heart of Milkomeda, shaping the future of what remains of our two galaxies. But for that to happen, the galaxies have to collide first, and they are already on their way. But for that collision to happen, the galaxies have to actually be moving toward each other. And this is where things get genuinely strange, because in a universe where almost everything is flying apart, where the space between distant galaxies is expanding at an accelerating rate, where the cosmic web is stretching and the horizon of the observable universe is receding faster every year, Andromeda is moving toward us. Not slowly, not tentatively, at 110 kilometers per second. Every second, the gap between our galaxy and Andromeda shrinks by 110 kilometers. That is not a typo. That is not an approximation. That is the measured radial velocity of Andromeda relative to the Milky Way, confirmed by decades of spectroscopic observations, cross-checked with multiple instruments, verified to within a few kilometers per second of uncertainty. Andromeda is approaching. And in a universe built on expansion, That approach is an exception worth understanding. Let's start with the expansion itself, because you cannot appreciate how weird Andromeda's motion is without first understanding what the rest of the universe is doing. In 1929, Edwin Hubble, the same astronomer who proved Andromeda was a separate galaxy, published a second groundbreaking discovery. He had been measuring the spectra of distant galaxies, looking at the light they emitted, and he noticed something consistent. Almost every galaxy he observed showed a redshift. Their light was stretched, shifted toward longer wavelengths, toward the red end of the spectrum. And the farther away a galaxy was, the more pronounced the redshift became. Hubble realized this was not a quirk of individual galaxies. Space itself was expanding, carrying the galaxies along with it, increasing the distance between any 2 points not held together by gravity. Imagine drawing dots on a deflated balloon and then inflating it. The dots do not move across the surface. The surface itself expands, and the distance between the dots grows. That is what the universe is doing, expanding uniformly in all directions, stretching the fabric of space and pulling distant galaxies away from each other at speeds that increase with distance. A galaxy 1 billion light-years away recedes slowly. A galaxy 10 billion light-years away recedes much faster. A galaxy near the edge of the observable universe recedes faster than the speed of light, not because it is moving through space faster than light, which would violate relativity, but because the space between us and that galaxy is expanding so rapidly that light leaving it now will never reach us, no matter how long we wait. This expansion is why the night sky is mostly dark. If the universe were static and infinite, every line of sight would eventually hit a star, and the sky would glow uniformly in every direction. But the universe is not static. It is expanding, and the light from the most distant stars has been stretched so far into the infrared and radio wavelengths that it becomes effectively invisible. The expansion also means that the universe has a history. If everything is moving apart now, then in the past, everything was closer together. Run the clock backward far enough, and you arrive at the Big Bang, the moment roughly 13.8 billion years ago when the universe was compressed into an unimaginably hot, dense state and then began expanding. We are still living in that expansion. It has never stopped. And current measurements suggest it is accelerating, driven by something astronomers call dark energy, a mysterious force that seems to be pushing space apart faster and faster as time goes on. That is the default state of the universe. Expansion, galaxies moving apart, space stretching, redshift. Almost every galaxy we observe participates in this. Almost. There are exceptions. Roughly 100 galaxies out of the hundreds of billions we can observe show blue shifts instead of red shifts. Their light is compressed, shifted toward shorter wavelengths, toward the blue end of the spectrum. That means they are moving toward us, not because the expansion has reversed locally, but because their motion through space, their actual velocity relative to us, is large enough to overcome the expansion. They are falling toward us under the influence of gravity, pulled inward by the combined mass of the Milky Way and everything else in our immediate neighborhood. Andromeda is one of those galaxies, the largest one, the closest one, and the one moving toward us faster than any other major galaxy in the observable universe. The blue shift in Andromeda's spectrum was first measured in 1912 by Vesto Slipher, an American astronomer working at Lowell Observatory in Arizona. Slipher was studying the spectra of spiral nebulae, the same objects that would later be identified as galaxies, and he was looking for motion. He found it. Andromeda's spectrum showed absorption lines that were shifted toward the blue, indicating the object was approaching at roughly 300 kilometers per second. That number included the motion of the Sun itself, which is orbiting the Milky Way's center at about 225 kilometers per second. Subtract the Sun's motion and you get Andromeda's radial velocity relative to the Milky Way, 110 kilometers per second, inward, directly toward us. That measurement held up. Decades of follow-up observations with better instruments, more sensitive spectrographs, longer integration times, all confirmed the same result. Andromeda is approaching. The blue shift is real, and the velocity is consistent. 110 kilometers per second is not the kind of speed you get from random motion. It is directed, sustained, and driven by something powerful. That something is gravity. Andromeda and the Milky Way are the two largest members of the local group, a collection of about 50 galaxies bound together by their mutual gravitational pull. The local group spans roughly 10 million light-years across, a relatively small region by cosmological standards, but large enough to contain a few dozen dwarf galaxies, a handful of irregular galaxies, and 3 major spirals: Andromeda, the Milky Way, and Triangulum. The rest are satellites, small systems orbiting the larger ones, held in place by gravity, unable to escape. The local group as a whole is gravitationally bound, which means it resists the expansion of the universe. The space inside the local group is not stretching. The galaxies inside are not being pulled apart by dark energy. They are held together by their own mass, orbiting a common center of gravity, interacting, merging, slowly collapsing inward over billions of years. Andromeda and the Milky Way dominate that collapse. Between them, they account for more than 90% of the local group's stellar mass and an even larger fraction of its dark matter. Their combined gravitational pull shapes the motion of everything nearby. Dwarf galaxies orbit them, smaller systems fall toward them, and the two giants pull on each other with a force that has been building for billions of years. That pull is what is driving Andromeda toward us. It is not a collision in the sense of two objects accidentally wandering into each other's paths. It is a gravitational inevitability, the final stage of a slow infall that began when the two galaxies first formed in the early universe. The details of that infall are written in the motion. 110 kilometers per second is the radial velocity, the component of Andromeda's motion, directly along the line of sight between us and the galaxy. But galaxies do not move in straight lines. They orbit, they drift sideways. They have tangential velocities, motion perpendicular to the line of sight, that affect their overall trajectory. For decades, astronomers could measure Andromeda's radial velocity with high precision, but the tangential component was much harder to pin down. You need to track the galaxy's position on the sky over many years, measuring how much it shifts sideways, and then calculate the angular velocity. That measurement is extraordinarily difficult because the shift is tiny. Andromeda is 2.5 million light-years away. Even at a sideways velocity of 100 kilometers per second, the galaxy would take thousands of years to move a distance on the sky equal to the width of a human hair held at arm's length. For most of the 20th century, astronomers could not measure that sideways motion. They knew Andromeda was approaching. They did not know whether it would hit us head-on, graze past us, or miss entirely. The uncertainty was large enough that some models predicted a near miss with no collision at all. That changed in 2012 when a team of astronomers published results from the Hubble Space Telescope. Hubble had been tracking the positions of stars in Andromeda's outer regions over a span of several years, measuring their tiny shifts on the sky with extraordinary precision. By combining those measurements with the known radial velocity, the team calculated Andromeda's full three-dimensional motion through space. The conclusion was stark. Andromeda was on a direct collision course with the Milky Way, not a near miss, a head-on impact. The two galaxies were going to merge, and the collision would begin in roughly 4 billion years. That announcement made headlines. A galaxy collision sounds dramatic, violent, apocalyptic, and in a sense it is, but the reality is more complicated, and we will get to that in the next chapters. For now, what matters is that the measurement settled a question astronomers had been arguing about for decades. Andromeda's tangential velocity was small. The galaxy was not drifting sideways fast enough to miss us. It was coming straight at us, aimed almost perfectly at the Milky Way's center, accelerating under mutual gravity, closing the gap with every passing second. The collision was not a possibility. It was, at that time, considered a certainty. Then came the revision. In 2025, a team led by Till Sawala at the University of Helsinki published a new analysis using data from the Gaia satellite and updated measurements from Hubble. Gaia, launched by the European Space Agency, had spent years mapping the positions and motions of more than 1 billion stars in the Milky Way with unprecedented precision. That data allowed astronomers to build better models of the Milky Way's mass distribution, its dark matter halo, and its gravitational influence on nearby galaxies. When Sawala's team fed that data into simulations of the local group, running 100,000 different scenarios with slightly varying initial conditions, they found something surprising. The collision was not as certain as the 2012 study had suggested. In fact, only about 50% of the simulations resulted in a merger within the next 10 billion years. The other 50% showed Andromeda and the Milky Way swinging past each other, missing by a wide enough margin that they would not merge until much later, if at all. That revision shocked a lot of people. For more than a decade, the collision had been treated as a done deal. Textbooks described it. Planetarium shows animated it. Popular science articles declared it inevitable. Now a new study was saying the odds were closer to a coin flip. What changed? Mostly the models. The 2012 study assumed the Milky Way and Andromeda were interacting in isolation, a simple two-body problem where two massive objects fall toward each other under mutual gravity. The 2025 study included additional factors. The gravitational influence of Triangulum, the third largest galaxy in the local group. The Large Magellanic Cloud, a dwarf galaxy currently falling into the Milky Way and expected to merge with us within the next billion years. The motion of other smaller satellites, the shape and distribution of the dark matter halos, all of those details change the trajectory slightly. And when you run simulations over billions of years, slight changes in the starting conditions can produce very different outcomes. Sawala's team found that in scenarios where the Large Magellanic Cloud merges with the Milky Way first, which is almost certain to happen, the extra mass changes the Milky Way's gravitational pull just enough to alter Andromeda's path. In some simulations, that change pushes the two galaxies into a closer, faster collision. In others, it deflects Andromeda slightly, turning a direct hit into a glancing blow. The odds depend on the exact timing of the Large Magellanic Cloud merger, the precise mass of Andromeda's dark matter halo, and the current distance and velocity of Triangulum, which is also interacting with Andromeda gravitationally and may merge with it before Andromeda reaches us. Triangulum sits about 250,000 light-years from Andromeda, close enough that tidal forces are likely pulling the two galaxies together. If they merge, the combined system will be more massive, and that extra mass will affect how quickly Andromeda falls toward the Milky Way. The upshot is that the dynamics of the local group are messy. 3 major galaxies, a dozen dwarf galaxies, dark matter halos overlapping at the edges, tidal forces stretching and distorting structures, orbits that take billions of years to complete. You cannot reduce that to a simple two-body problem. You have to model everything, Run the simulations thousands of times with slightly different inputs and see what patterns emerge. Sofala's simulations suggest the chance of a head-on collision within the next 4 to 5 billion years is only about 2%. Most of the merger scenarios happen later, after multiple close passes, with the galaxies swinging around each other, losing energy to tidal interactions, and gradually spiraling inward over 10 or even 15 billion years. A direct hit in 4 billion years, the scenario painted by the 2012 study, is possible but unlikely. That does not mean the collision is not happening. It just means the timeline is uncertain and the path is more complicated than a straight line. Andromeda is still approaching. The blue shift is still there. The radial velocity is still 110 kilometers per second. Gravity is still pulling the two galaxies together. The question is not whether they will interact. The question is when, how close, and how violent. 50% chance of a merger within 10 billion years means there is also a 50% chance they miss on the first pass, swing past each other, and take another few billion years to come back around. Either way, the outcome is the same eventually. Two massive galaxies bound by gravity, orbiting a common center of mass, losing energy with each pass, spiraling inward until they merge. The time scale might be longer than we thought. The path might be less direct. But the end result has not changed. Triangulum complicates the picture further. M33, as it is catalogued, weighs roughly 60 billion solar masses, about a tenth of the Milky Way's mass and a fraction of Andromeda's. But it is close enough to both galaxies that its gravity matters. Some models suggest M33 is already bound to Andromeda, orbiting the larger galaxy on a long elliptical path. Others argue M33 is independent, moving through the local group on its own trajectory, and the current proximity to Andromeda is temporary. If M33 is bound to Andromeda, then when Andromeda falls toward the Milky Way, M33 comes along for the ride. If M33 is independent, it might merge with the Milky Way first, or it might get flung out of the local group entirely during the chaos of the Andromeda-Milky Way collision. The simulations do not agree. Roughly 63% of the scenarios show M33 eventually merging with either Andromeda or the Milky Way. The other 37% show it getting ejected, thrown out of the local group by gravitational interactions, sent wandering into intergalactic space where it will drift alone for billions of years, slowly fading as its gas is exhausted and star formation shuts down. The gravitational interplay between these three galaxies is what dictates the collision course. Andromeda pulls on the Milky Way. The Milky Way pulls on Andromeda. Triangulum pulls on both. The Large Magellanic Cloud pulls on the Milky Way. Dark matter halos overlap and interact. Every piece of mass in the local group contributes to the overall gravitational field, and that field is constantly shifting as galaxies move, merge, and change their positions. The result is a slow dance, a cosmic ballet playing out over billions of years, with trajectories that curve and shift in response to every interaction. You cannot predict the exact outcome without knowing the initial conditions to absurd precision, and we do not have that precision. We know Andromeda's position to within a few thousand light years. We know its velocity to within a few kilometers per second. Those uncertainties are tiny by everyday standards. They are enormous when you are trying to predict where a galaxy will be in 4 billion years. What we can say with confidence is that Andromeda's approach is real, measurable, and ongoing. The blue shift is not an illusion. The radial velocity is not a fluke. The two galaxies are falling toward each other under mutual gravity, and that fall has been happening for billions of years. Long before Earth formed, Andromeda was already on this path, already moving toward the region of space where the Milky Way would eventually sit. Long before the first stars ignited in our galaxy, the seeds of this collision were set in motion by the initial distribution of matter in the early universe. Regions that were slightly denser than average collapsed under their own gravity, forming the first dark matter halos. Those halos attracted gas. The gas formed stars. The stars formed galaxies. And those galaxies, born in close proximity, have been pulling on each other ever since. The motion is slow by human standards, but relentless by cosmic ones. 110 kilometers per second sounds fast until you realize it takes 2.5 million years for light to travel from Andromeda to Earth. At Andromeda's current velocity, closing that distance will take billions of years. The galaxy is not going to arrive tomorrow. It is not going to arrive in your lifetime, or your children's lifetimes, or the lifetimes of any organism currently alive on this planet. But it is coming, and every second that passes, the distance shrinks by another 110 kilometers. Every hour, 400,000 kilometers. Every day, nearly 10 million kilometers. Every year, 3.5 billion kilometers. Over the course of a single human lifetime, Andromeda closes the gap by roughly 250 billion kilometers. That is more than the distance from the Sun to Pluto, traversed in the span of 70 years, and you would never notice. The galaxy looks the same in the sky tonight as it did the night you were born. It will look the same the night you die. The motion is there, constant and inexorable, but the scale is so vast that human perception cannot register it. That is what makes this collision both fascinating and unsettling. It is happening right now. The galaxies are already interacting gravitationally, already pulling on each other, already committed to a course that will end in a merger. And yet, from our perspective, nothing is changing. Andromeda sits in the same patch of sky, glowing faintly, visible on clear autumn nights, exactly where it has always been. The light reaching your eyes tonight left Andromeda 2.5 million years ago, long before modern humans existed. By the time that light arrives, it carries information about a galaxy that no longer exists in the state we are seeing. Andromeda today, the Andromeda that exists right now in real time, is slightly closer, slightly brighter, and slightly larger than the Andromeda we observe. We are seeing the past. We are always seeing the past. And the Andromeda of the past is telling us, through the blue shift in its spectrum, that it is on its way. The approach is unstoppable because gravity is relentless. There is no force that can reverse it, no mechanism that can push the two galaxies apart. Dark energy expands the universe on the largest scales, but inside the local group, gravity dominates. The mutual pull between Andromeda and the Milky Way is stronger than the expansion, and it will remain stronger until the merger is complete. Once two objects are gravitationally bound, once they are falling toward each other with enough velocity to overcome the expansion, the outcome is determined. They will collide. The timing might shift, the path might curve, but the end result is written in the equations. So Andromeda is coming, not because it wants to, not because something pushed it, because gravity, patient and indifferent, has been pulling it toward us since the beginning. And now, after billions of years of slow acceleration, the two galaxies are close enough that the collision is not a distant abstraction. It is a countdown, a clock ticking down toward an event that will reshape everything we think we know about our place in the cosmos. The 4.5 billion year countdown, a cosmic clock 4.5 billion years. That is the number you will see in most recent scientific papers, press releases and astronomy textbooks when they talk about when Andromeda and the Milky Way will collide. 4.5 billion years from now. Not 4 billion, not 5 billion, 4.5. The precision is deliberate. the result of decades of observation, modeling, and computational work, and it is also, in a very real sense, meaningless. Not because the scientists are wrong, they are not. The models are good. The simulations are sophisticated. The data is solid. But 4.5 billion years is not a date circled on a cosmic calendar. It is an estimate derived from probabilities, pulled from tens of thousands of simulated scenarios where researchers tweaked every variable they could think of and watched what happened. The truth is messier than a single number suggests. The collision is not an event that will happen at a specific moment. It is a process that will unfold over hundreds of millions of years, with a starting point that depends on how you define the word collision, and an endpoint that depends on what you consider merged. Saying the galaxies will collide in 4.5 billion years is like saying 2 hurricanes will collide next Tuesday. Technically accurate if you squint, but it misses the complexity of what is actually happening. Let's unpack that number. Where does it come from? Start with the basics. Andromeda is currently 2.5 million light-years away, moving toward us at 110 kilometers per second. If you treat that as a simple physics problem, an object moving at constant velocity over a known distance, you can calculate how long it takes to close the gap. Divide 2.5 million light-years by 110 kilometers per second, convert the units, and you get roughly 22 billion years. That is how long it would take Andromeda to reach us if it were moving in a straight line at a constant speed through empty space with no other forces acting on it. It is also completely wrong, because gravity does not work that way. Andromeda is not coasting. It is accelerating. The closer it gets, the stronger the gravitational pull between the two galaxies becomes, and the faster Andromeda moves. Think of it like dropping a ball from a tall building. The ball does not fall at a constant speed. It accelerates as it drops, pulled harder and harder by gravity the closer it gets to the ground. Andromeda is doing the same thing, falling toward the Milky Way under mutual gravitational attraction, picking up speed as the distance shrinks. That acceleration changes everything. Instead of 22 billion years, the time to collision drops dramatically. Early estimates in the 1990s based on simple two-body models where you assume the Milky Way and Andromeda are the only objects in the universe and calculate their trajectories under mutual gravity put the collision at roughly 3 to 4 billion years from now. Then better data came in. In 2012, a team led by Roland van der Marel at the Space Telescope Science Institute published the first precise measurement of Andromeda's tangential velocity, the component of its motion perpendicular to our line of sight. That measurement was critical because it told astronomers whether Andromeda was heading straight at us or drifting sideways. If the tangential velocity was large, Andromeda might miss us entirely, swinging past the Milky Way like a comet grazing the Sun and flying back out into intergalactic space. If the tangential velocity was small, a head-on collision was inevitable. Van der Marel's team used the Hubble Space Telescope to track the positions of individual stars in Andromeda's outer halo over a span of 5 to 7 years. The shifts were tiny, measured in milliarseconds, angles so small that they are equivalent to watching a person walk on the moon from Earth and measuring how much they move. Hubble could do it, barely. The result was clear. Andromeda's tangential velocity was small, very small, consistent with zero within the margin of error. The galaxy was not drifting sideways, it was coming almost directly at us. Van der Marel's team ran simulations using those measurements, feeding the data into gravitational models, running the clock forward billions of years to see what would happen. Their conclusion was stark. Andromeda and the Milky Way would collide in approximately 3.9 billion years. Not a glancing blow, not a near miss, a direct hit. The two galaxies would pass through each other, their stars and gas clouds intermingling, their structures distorted by tidal forces, and then they would swing back around, pass through each other again, and eventually merge into a single elliptical galaxy over the course of roughly 6 billion years total. The collision was no longer a possibility, it was a certainty. That certainty lasted about 13 years. In 2025, a new study led by Till Sawala at the University of Helsinki used updated data from the Gaia satellite, which had spent years mapping the positions and motions of more than 1 billion stars in the Milky Way with unprecedented precision. Gaia's data allowed astronomers to build much more accurate models of the Milky Way's mass, its dark matter halo, and the gravitational influence of other nearby galaxies. Sawala's team ran 100,000 simulations of the local group, varying the starting conditions slightly each time to account for uncertainties in the measurements. They included not just the Milky Way and Andromeda, but also Triangulum, the Large Magellanic Cloud, and more than a dozen smaller dwarf galaxies. Every piece of mass in the local group contributes to the overall gravitational field, and every contribution changes the trajectory slightly. The results were surprising. Only about 50% of the simulations resulted in a merger between Andromeda and the Milky Way within the next 10 billion years. In the other 50%, the galaxies swung past each other on the first approach, missing by a wide enough margin that they did not merge until much later, if at all. Some scenarios showed the galaxies passing within 500,000 light-years of each other, close enough to distort each other's shapes but not close enough to trigger a full merger. In those cases, the galaxies would loop outward, slow down, and eventually fall back together for a second pass billions of years later. When Sawala's team restricted the simulations to scenarios that resulted in a head-on collision within the next 4 to 5 billion years, the kind of event van der Marel's 2012 study had predicted, they found only about 2% of the simulations matched that outcome. 2%. The rest either resulted in a later merger after multiple passes or no merger at all within the time frame of the simulation. That does not mean the collision is not happening. It means the path is more complicated than a straight line, the timing is more uncertain than a single number, and the outcome depends on factors we cannot measure precisely enough to predict with confidence. So where does 4.5 billion years come from? It is the median result from those simulations. Half the scenarios that result in a merger show it happening before 4.5 billion years. Half show it happening after. It is a statistical midpoint, not a deadline. If you ran the simulation with slightly different starting conditions, tweaked the mass of Andromeda's dark matter halo by 10%, or adjusted the distance to Triangulum by 50,000 light-years, the median would shift. Maybe it becomes 4 billion years, maybe it becomes 5 billion. The uncertainty is large enough that pinning down the exact moment of collision is impossible with current data. What we can do is break the process into stages and estimate when each stage is likely to begin. Stage 1 is already happening. The gravitational interaction between Andromeda and the Milky Way is not something that starts when the galaxies touch. It is happening right now. The two galaxies are already pulling on each other across 2.5 million light-years of space, accelerating toward each other, distorting each other's dark matter halos at the edges. The effect is subtle, undetectable without extremely precise measurements of star motions near the outer edges of each galaxy's halo, but it is real. Gravity does not wait for contact. It reaches across the void and starts shaping trajectories long before anything collides. Stage 2 begins when the tidal forces become strong enough to visibly distort the galaxies. This will not happen until Andromeda gets much closer, probably within a few 100,000 light-years. At that distance, the gravitational pull from Andromeda will start stretching the outer regions of the Milky Way, pulling stars and gas clouds outward in long tidal tails that stream toward the approaching galaxy. The same thing will happen to Andromeda. Its outer spiral arms will start to warp, bend and stretch in response to the Milky Way's gravity. The galaxies will still be separate structures, but their shapes will no longer be clean spirals. They will look distorted, twisted, pulled out of alignment. Deep sky images taken billions of years from now would show two galaxies that are clearly interacting, their edges blurred, their arms reaching toward each other like fingers trying to touch. This stage will likely begin somewhere between 3 and 4 billion years from now, maybe sooner if the galaxies are moving faster than current models predict, maybe later if they are moving slower or if their approach is more tangential than we think. The uncertainty is large, but once tidal distortion starts, it accelerates. The closer the galaxies get, the stronger the tidal forces become, and the more dramatic the distortion. By the time Andromeda is within 1 million light-years, the Milky Way will no longer look like a spiral. It will look like something being torn apart. Stage 3 is the first close pass. This is when the two galaxies actually interpenetrate, when their outer regions overlap and their stars begin moving through each other. This will happen roughly 4 to 4.5 billion years from now in most scenarios. The word collision is misleading here because individual stars will not collide. Space is mostly empty. The distance between stars is so vast compared to their size that even when two galaxies pass through each other, the chance of any two stars actually hitting is effectively zero. Think of it this way. If the Sun were the size of a ping-pong ball, the nearest star, Proxima Centauri, would be another ping-pong ball sitting 3,200 kilometers away. That is roughly the distance from New York to Los Angeles. Now imagine two collections of ping-pong balls, each spread out over millions of kilometers, passing through each other. The balls are moving fast, but the space between them is so enormous that almost none of them touch. That is what happens when galaxies collide. The stars pass through like ghosts, barely noticing each other. But the gas does not pass through. Gas clouds are large, diffuse, and when they collide, they heat up, compress, and trigger massive bursts of star formation. Everywhere two gas clouds meet, new stars will ignite, forming in clusters so dense and so bright that they will outshine everything else in the merging galaxies. The rate of star formation during a galaxy merger can increase by a factor of 10 or more compared to normal background rates. Astronomers call this a starburst, and it is one of the most energetic processes in the universe. The newly formed stars will be hot, blue and short-lived massive giants that burn through their fuel in just a few million years before exploding as supernovae. Those explosions will seed the surrounding gas with heavy elements, enriching the next generation of stars, and the cycle will continue. The first close pass will also distort the galaxies even more dramatically. Tidal forces will rip material from both systems, flinging stars and gas outward in long streamers that extend hundreds of thousands of light-years into space. Some of that material will fall back into the galaxies during later passes. Some will be ejected permanently, lost to intergalactic space, wandering alone for billions of years until it either falls into another galaxy or fades into darkness. Computer simulations of galaxy mergers show these tidal tails forming almost immediately after the first pass, curving gracefully away from the collision site like the arms of a spiral galaxy turned inside out. After the first pass, the galaxies will separate. They will not merge on the first encounter. Instead, they will swing past each other, slow down as gravity pulls them back, and then fall inward again for a second pass. This process is called dynamical friction, and it is how galaxy mergers work. Each pass removes energy from the system. The galaxies lose orbital energy to gravitational interactions with stars, gas clouds, and dark matter particles, and that lost energy causes their orbits to decay. With each pass, they get closer. With each pass, the tidal forces get stronger. With each pass, more material is stripped away, more stars are flung into the outer regions, and more gas is funneled toward the centers where the supermassive black holes sit. Stage 4 is the second pass, which will happen a few 100 million years after the first. By this point, the two galaxies will no longer look like separate objects. They will be a chaotic tangle of stars, gas, and dust, their structures so distorted that identifying where one galaxy ends and the other begins will be impossible. The spiral arms will be gone, shredded by tidal forces. The disks will be warped, thickened, and puffed up into irregular shapes. And the centers, the dense cores where most of the stars are concentrated, will be sinking toward each other, pulled inward by gravity, losing energy with every orbit. Stage 5 is the final merger. This happens when the two galactic cores finally meet, when the supermassive black holes at their centers spiral inward and combine. That process takes a long time, possibly hundreds of millions of years, because black holes lose orbital energy very slowly. They have to interact with surrounding stars, flinging them outward in gravitational slingshots, and each interaction removes a tiny amount of energy from the black hole's orbit. Eventually, the black holes get close enough that gravitational waves take over. Gravitational waves are ripples in space-time itself, emitted by any accelerating mass, and they carry energy away from the system. For small objects, the energy loss is negligible. For two black holes weighing millions of solar masses each, spiraling around each other at a significant fraction of the speed of light, the energy loss is enormous. In the final moments before the black holes merge, they will lose mass equivalent to several suns' worth of energy, radiated away as gravitational waves in a pulse, so powerful that it will be detectable by any civilization within 1 billion light-years that has the instruments to listen. When the black holes merge, the resulting object will weigh roughly 104 million solar masses, slightly less than the sum of the two originals, because a few million solar masses worth of energy will be radiated away during the merger. That merged black hole will sit at the center of the new galaxy, surrounded by a dense core of stars, most of them old and red, packed so tightly that the night sky from a planet in that region would be filled with thousands of stars brighter than Venus. The new galaxy will be an elliptical, a smooth, featureless blob of stars with no spiral arms, no disk, no organized structure. Just a vast cloud of stars orbiting a common center, slowly relaxing into a spherical shape over billions of years as gravitational interactions smooth out any remaining asymmetries. The entire process, from first close pass to final merger, will take somewhere between 2 and 3 billion years. Add that to the 4.5 billion years it takes for the galaxies to reach each other, and you get a total timeline of roughly 6 to 7 billion years from now until the merger is complete. That is the number astronomers quote when they talk about when Milkomeda, the name given to the merged galaxy, will fully form. 6 billion years, maybe 7, maybe 5 if things move faster than expected. The uncertainty is built into the physics. You cannot predict the exact behavior of 1 trillion stars interacting gravitationally over billions of years. You can only run simulations, average the results, and accept that the real universe will do something slightly different from any single model. What makes this timeline even more uncertain is the influence of other galaxies. The Large Magellanic Cloud, a dwarf galaxy currently orbiting the Milky Way, will almost certainly merge with us within the next billion years. When it does, the extra mass will change the Milky Way's gravitational pull, which will change Andromeda's trajectory, which will change the timing of the collision. Triangulum, the third largest galaxy in the local group, is also a wildcard. If it merges with Andromeda first, which some models predict, the combined system will be more massive, and the collision with the Milky Way will happen sooner and more violently. If Triangulum merges with the Milky Way instead, or if it gets ejected from the local group entirely during the chaos, the timeline shifts again. Every dwarf galaxy, every star cluster, every cloud of gas drifting through the local group contributes to the gravitational field, and every contribution nudges the trajectories slightly. The simulations account for this by running tens of thousands of scenarios with different starting conditions. Some scenarios show a head-on collision in 4 billion years. Some show a glancing blow in 5 billion. Some show multiple passes over 10 billion years. The 4.5 billion year estimate is just the median, the point where half the scenarios fall on one side and half fall on the other. It is not a prediction, it is a probability. And yet, despite all the uncertainty, despite the complexity of the models and the limitations of the data, one thing is clear: the countdown is real. Whether it takes 4 billion years or 5 billion or 10, Andromeda and the Milky Way are on a path that ends in a merger. The clock is ticking. It has been ticking since the two galaxies first formed in the early universe, since the initial distribution of matter set them on converging trajectories, since gravity began pulling them together across the void. And it will keep ticking, second by second, year by year, billion by billion, until the moment when two spiral galaxies collide and something new is born. 4.5 billion years is a long time to wait for an answer, but the answer, when it finally arrives, will not be subtle. Two massive spiral galaxies, each containing hundreds of billions of stars, each wrapped in dark matter halos stretching hundreds of thousands of light years into space, will collide, merge, and transform into something neither galaxy was before. The result has a name. Astronomers call it Milkomeda. A portmanteau that sounds vaguely ridiculous until you remember it, describes the most significant event that will ever happen to our corner of the universe, the birth of a new galaxy from the wreckage of two old ones. The name is informal, coined by researchers who needed a shorthand way to refer to the merged system in their papers and simulations. It stuck. Some astronomers prefer the alternative Milkomeda, which rolls off the tongue slightly better but has not gained the same traction in the literature. Either way, the name is a placeholder for something we have never directly observed, a galaxy in the process of being born. We have seen plenty of galaxy mergers at various stages of completion, scattered across the sky at distances ranging from a few million to a few billion light-years. Some are just beginning, two spirals approaching each other with their structures still intact. Others are midway through, their shapes distorted into chaotic tangles of stars and gas. And some are nearly finished, smooth elliptical galaxies that show no trace of the spiral arms they once had. Milkomeda will follow that same path. It will be messy, violent, and spectacular. And by the time it is finished, roughly 6 to 10 billion years from now, depending on whose simulations you trust, the Milky Way and Andromeda will no longer exist as separate objects. They will be one galaxy. An elliptical giant. Smooth, featureless, and ancient. Elliptical galaxies are the retirement homes of the universe. They are what happens when spiral galaxies stop forming new stars, exhaust their gas supplies, and settle into a stable configuration where nothing dramatic happens anymore. Most ellipticals are old, their stellar populations dominated by red and yellow stars that formed billions of years ago and have been quietly orbiting the galactic center ever since. There are no spiral arms, no disks, no organized structure, just a smooth blob of stars, roughly spherical or slightly elongated, glowing with a warm reddish light that signals age and exhaustion. Ellipticals do not rotate the way spirals do. Spirals have disks where stars move in orderly circular orbits, all rotating in the same direction like a spinning record. Ellipticals have no disk. The stars move on random elliptical orbits, some tilted one way, some tilted another, their motions scrambled by billions of years of gravitational interactions. The result is a galaxy that looks the same from almost any angle. Turn it, rotate it, view it from the side or from above, and it still looks like a glowing ball of stars. Boring, maybe, but stable. Milkomeda will be a massive elliptical, not just large, massive. It will contain well over 1 trillion stars, the combined stellar populations of the Milky Way and Andromeda, plus whatever new stars form during the merger itself. That number is hard to grasp. 1 trillion is a 1 followed by 12 zeros. If you tried to count to 1 trillion, spending 1 second on each number, it would take you more than 31,000 years. That is how many stars will be packed into Milkomeda, and most of them will be old. The Milky Way's stars are already billions of years old on average. Andromeda's are similar. By the time the merger completes, those stars will be even older, and very few new stars will be forming because the gas will be gone. That is one of the defining features of elliptical galaxies. They have no gas, or rather, they have very little gas compared to spirals. Spiral galaxies like the Milky Way and Andromeda are rich in hydrogen, the raw material for star formation. Vast clouds of cold hydrogen drift through the spiral arms, collapsing under their own gravity, fragmenting into clumps, and igniting as new stars. That process has been running continuously for billions of years, replenishing the stellar population, creating new generations of stars to replace the ones that die. Ellipticals do not do that. They ran out of gas long ago, or they lost it, or it was heated to temperatures too high for star formation to occur. Without gas, there is no star formation. Without star formation, the galaxy slowly fades as its stars age, cool, and die. Ellipticals are not dead. They are just not making anything new. Milkomeda will lose its gas during the merger. Not all of it, but most of it. Every time the Milky Way and Andromeda pass through each other, their gas clouds will collide. Gas clouds are large, diffuse, and when they meet, they do not pass through like stars do. They crash, compress, and heat up. The collision compresses the gas to densities high enough to trigger runaway star formation, and for a few 100 million years, the merger will light up with brilliant blue stars, massive hot giants that burn through their fuel in just a few million years. Astronomers call this a starburst, and it is one of the most energetic phases in the life of a galaxy. The star formation rate during a starburst can be 10 times higher than normal, maybe more. Entire clusters of stars will ignite simultaneously, shining so brightly that they outshine everything else in the merging system. But starbursts do not last. The massive stars that form during a starburst die quickly. They explode as supernova, blasting their outer layers into space, heating the surrounding gas to millions of degrees and driving powerful winds that push gas out of the galaxy entirely. Each supernova adds energy to the system, and after a few 100 million years of continuous explosions, the gas that has not already formed stars gets blown away. Some of it escapes into intergalactic space, lost forever. Some of it falls back inward billions of years later, but by then the starburst is over. The gas reservoir is depleted, star formation shuts down, and the galaxy transitions from an active star-forming spiral to a quiet, aging elliptical. That is Milkomeda's fate. The merger will trigger one final burst of star formation, a last hurrah before the gas runs out. And then, silence. No more blue stars. No more massive giants, just the slow cooling of the stellar population as the oldest stars evolve into red giants, shed their outer layers and fade into white dwarfs. The galaxy will dim over billions of years, shifting from a bright bluish white during the starburst to a warm yellow a few billion years later to a deep reddish orange 10 billion years after that. By the time Milkomeda reaches old age, 50 or 100 billion years from now, it will be a dim red ghost, barely visible against the blackness of intergalactic space, its stars exhausted, its black hole dormant, its structure frozen in a configuration that will persist until the universe itself ends. But we are getting ahead of ourselves. Before Milkomeda becomes a quiet elliptical, it has to finish forming. And that process is anything but quiet. The simulations show it clearly. When two spiral galaxies collide, the first thing that happens is chaos. The smooth, orderly structure of both galaxies gets shredded. Spiral arms twist, warp, and stretch into long tidal tails. Stars and gas clouds get flung outward at high velocities, some of them reaching escape velocity and leaving the system entirely. The disks, those flat rotating structures where most of the stars live, get puffed up, thickened, and distorted until they no longer look like disks at all. And the cores, the dense central regions where the supermassive black holes sit, sink toward each other, spiraling inward over hundreds of millions of years until they meet. The stars themselves do not collide. This is worth repeating because the mental image of a galaxy collision often involves stars smashing into each other, exploding, scattering debris across space. That does not happen. Space is too empty. The average distance between stars in the Milky Way is about 4 light-years. That is roughly 40 trillion kilometers. Stars are tiny compared to that distance. The Sun is about 1.4 million kilometers in diameter. If you scaled the galaxy down so that the Sun was the size of a grain of sand, the nearest star would be another grain of sand sitting about 10 kilometers away. Now imagine 2 handfuls of sand, each containing hundreds of billions of grains, thrown at each other. The grains pass through like ghosts. Almost none of them touch. That is what happens when galaxies collide. The stars pass through, their orbits bent and scrambled by the gravitational field of the other galaxy, but direct collisions are extraordinarily rare. Maybe one star in the entire merged system will physically collide with another. Maybe. Probably not even that. What does happen is orbital reshuffling. Every star in the Milky Way is currently on a relatively stable orbit around the galactic center. Some orbits are circular, some are elliptical, but they are all organized, all rotating in roughly the same direction. That organization gets destroyed during the merger. As Andromeda's gravity pulls on the Milky Way's stars, their orbits get bent, twisted, and redirected. Stars that were orbiting in the plane of the disk get kicked into highly elliptical orbits that take them far above and below the plane. Stars that were moving in orderly circular paths get scattered onto chaotic trajectories that crisscross the galaxy at random angles. By the time the merger is complete, the orderly rotation of the original spirals is gone, replaced by a chaotic swarm of stars moving in every direction. That swarm, once it settles down and stops evolving, is an elliptical galaxy. The Sun will be one of those scattered stars. Right now, the Sun sits about 26,000 light-years from the center of the Milky Way, orbiting at a speed of roughly 220 kilometers per second. It completes one orbit every 230 million years. That orbit is relatively circular, relatively stable. The Sun has been following a similar path for billions of years. and if nothing disturbed the Milky Way, it would continue following that path for billions more. But something is about to disturb the Milky Way. When Andromeda arrives, the Sun's orbit will change. Maybe it gets kicked outward, flung into the outer halo where stars are sparse and the distances between them stretch to tens of light years. Maybe it gets pulled inward, dragged closer to the galactic center where the stellar density is higher and the night sky is crowded with thousands of bright stars. Or maybe, and this is one of the stranger possibilities, the Sun gets captured by Andromeda during one of the early passes, pulled away from the Milky Way entirely and incorporated into Andromeda's structure before the two galaxies fully merge. Simulations show that a small fraction of stars, maybe 1 or 2%, can jump ship during a galaxy merger. They get caught in the tidal tails, the long streamers of stars and gas that get pulled out of both galaxies during the collision, and they end up in strange transitional orbits that technically belong to both galaxies at once. Some of those stars eventually fall back into the merged system. Others get ejected entirely, flung out of the local group at high velocity, destined to wander alone through intergalactic space for the rest of their lives. The Sun could be one of those stars. Unlikely, but possible. The odds are low enough that it is not worth worrying about. But it is worth acknowledging that the Sun's position in the galaxy, its place in the cosmic neighborhood, is not permanent. It is contingent on the stability of the Milky Way's structure, and that structure is about to be shredded. The central supermassive black holes will also merge, eventually. That process takes longer than you might expect because black holes, despite their reputation, are surprisingly inefficient at finding each other. When the two galaxies first collide, the black holes are separated by millions of light years. As the galaxies pass through each other multiple times, losing energy to tidal interactions, the black holes sink toward the center of the merged system, dragged inward by dynamical friction. Dynamical friction is the process by which a massive object moving through a sea of smaller objects, in this case stars, loses energy by gravitationally interacting with those objects. Each interaction flings a star outward at high velocity, and by conservation of momentum, the black hole loses a tiny amount of energy and sinks slightly deeper into the gravitational well. This process is slow. It takes hundreds of millions of years for the black holes to sink from the outer regions of the merged galaxy to the center. Once they get close, within a few light years of each other, dynamical friction becomes less effective because there are fewer stars nearby to interact with. At that point, the black holes have to interact directly with each other, spiraling inward on tighter and tighter orbits, gradually losing energy to gravitational waves. Gravitational waves are ripples in space-time itself, emitted by any accelerating mass, and they carry energy away from the system. For small objects, the energy loss is negligible. For two supermassive black holes weighing millions of solar masses each, spiraling around each other at relativistic speeds, the energy loss is enormous. In the final moments before the black holes merge, when they are orbiting each other at a distance of just a few times their event horizons, they will lose energy at a rate equivalent to the power output of 10 quintillion suns. 10 quintillion. That is a 1 followed by 19 zeros. More energy than every star in the observable universe produces combined. And all of that energy is radiated away as gravitational waves in a pulse that lasts less than a second. Observatories on Earth, assuming humanity still exists and still operates gravitational wave detectors billions of years from now, will detect that pulse. It will be the loudest gravitational wave event ever recorded, a signal so strong that it will be detectable by any civilization within 1 billion light years that has the instruments to listen. When the black holes finally merge, The resulting object will weigh roughly 104 million solar masses. That is the combined mass of the Milky Way's black hole, Sagittarius A star, which weighs about 4 million solar masses, and Andromeda's black hole, which weighs about 100 million solar masses, minus a few million solar masses that get radiated away as gravitational waves during the final in-spiral. The merged black hole will sit at the center of Milkomeda, surrounded by a dense core of stars, most of them old and red, scattered inward during the chaotic interactions of the merger. That core will be one of the densest regions in the local group, packed with stars so tightly that the average distance between them is measured in light-weeks instead of light-years. Planets orbiting stars in that region would have spectacular night skies, thousands of stars brighter than Venus, visible even during the daytime. Dozens of stars bright enough to cast shadows at night. The sky would never be truly dark. And the gravitational interactions between stars would be strong enough to occasionally perturb planetary systems, kicking planets out of their orbits, sending them wandering into interstellar space or crashing into their parent stars. It would be a beautiful but unstable place to live. The merged black hole will not stay quiet forever. Black holes grow by accreting matter, and there will be plenty of matter available after the merger. Gas funneled inward during the collision, stars on unstable orbits that wander too close and get torn apart by tidal forces, smaller black holes left over from the merger that have not yet coalesced with the central object. All of that material will feed the black hole over billions of years, causing it to grow. Slowly at first, then faster as more material falls in. If enough gas accumulates near the black hole, forming a dense accretion disk, the disk will heat up to millions of degrees and begin emitting intense radiation, turning Milkomeda into an active galactic nucleus, not as powerful as a quasar, probably, but bright enough to outshine the combined light of every star in the galaxy. That phase, if it happens, will last a few 100 million years before the gas runs out and the black hole goes dormant again. Milkomeda will also be surrounded by tidal debris, long streamers of stars and gas pulled out of both galaxies during the merger, stretching hundreds of thousands of light-years into intergalactic space. Some of that debris will fall back into the galaxy over billions of years, raining down onto the outer halo, adding mass to the system. Some will escape entirely, forming faint diffuse clouds that drift through the local group, slowly dispersing until they become too faint to detect. And some will clump together under their own gravity, forming small dwarf galaxies, tiny satellite systems that orbit Milkomeda like the Magellanic Clouds orbit the Milky Way today. Those dwarf galaxies will be the remnants of the merger, fragments of the original spirals that got torn off during the collision and never fell back in. The local group itself will change. Right now, the local group is a loose collection of about 50 galaxies, dominated by the Milky Way and Andromeda, with Triangulum as a distant third. After the merger, Milkomeda will be the only major galaxy left. Triangulum might merge with Milkomeda as well, or it might get ejected, flung out of the local group during the chaos, and sent wandering into intergalactic space. The dwarf galaxies, those small systems currently orbiting the Milky Way and Andromeda, will mostly get absorbed, swallowed whole by the growing elliptical. A few might survive, scattered into distant orbits, but most will fall inward and disappear into Milkomeda's halo, their stars mixed into the larger population until their original identity is lost. The escape velocity from the local group will increase. Right now, the escape velocity, the speed you would need to leave the local group entirely and never fall back, is about 550 kilometers per second. After the merger, when all the mass is concentrated into a single massive elliptical, that escape velocity will rise. How much depends on the total mass of Milkomeda and how it is distributed, but estimates put it somewhere around 600 or 700 kilometers per second. That might not sound like a big increase, but it matters if you are trying to send a spacecraft to another galaxy. The higher the escape velocity, the more energy you need to leave the system. For a civilization trying to explore intergalactic space, that extra energy requirement could be the difference between feasible and impossible. Milkomeda will be enormous, not just in mass, but in physical size. The stellar halo, the diffuse cloud of old stars orbiting the galactic center, will extend at least 1,000,000 light-years from the core. That is more than 10 times the radius of the Milky Way's current halo. The central region, the dense elliptical core where most of the stars are concentrated, will span roughly 200,000 light-years, about twice the diameter of the Milky Way's disk. And the dark matter halo, the invisible structure that holds the galaxy together, will reach even farther, possibly stretching 2 or 3 million light-years into space. Milkomeda will dominate the local group in a way that neither the Milky Way nor Andromeda ever did individually, but it will be lonely. Elliptical galaxies are not places where interesting things happen. They do not form new stars. They do not have spiral arms where gas clouds collapse and planets form. They do not have disks where solar systems orbit in orderly configurations. They are just vast collections of old stars, slowly cooling, slowly fading, drifting through space on random orbits that never settle into anything organized. Milkomeda will be stable, yes, but that stability comes at the cost of activity. Nothing new will be born. Nothing will evolve. The galaxy will simply exist, unchanging, for billions upon billions of years, until the last stars burn out, and the black hole at its center is the only thing left, sitting alone in the dark, radiating faint Hawking radiation for an unimaginable span of time before it too evaporates into nothing. That is the ultimate fate of Milkomeda. But before it reaches that quiet end, before the stars fade and the gas runs out, there will be a period of chaos, a time when two galaxies collide, their structures torn apart, their stars scattered, their gas ignited into one final burst of creation. And somewhere in the middle of that chaos, on a planet orbiting a star that may or may not survive the merger intact, life will look up at the sky and see something it has never seen before. A galaxy, bright and distorted, stretching across the heavens, close enough to resolve individual stars, close enough to see the glow of newly formed clusters, close enough to watch the collision unfold in real time. That sky will be terrifying and beautiful in equal measure, and it will be the last chapter of a story that began billions of years ago when two galaxies first started falling toward each other across the void. Earth's fate, surviving the cosmic maelstrom that merged black hole, will sit at the center of Milkomeda, surrounded by a dense core of stars, most of them old and red, scattered inward during the chaotic interactions of the merger. That core will be one of the densest regions in the local group, packed with stars so tightly that the average distance between them is measured in light weeks instead of light years. And somewhere in the middle of that chaos, assuming it still exists, will be our solar system. A single star, 8 planets, a handful of moons, and a thin shell of rock and ice drifting through the outer reaches, insignificant on the scale of galaxies, irrelevant to the physics of the merger. But if you happen to be standing on one of those rocks, if you happen to be looking up at the sky as Andromeda approaches, the question of what happens next stops being academic and becomes deeply, uncomfortably personal. Will Earth survive? Will the Sun survive? Will the solar system hold together, or will it be torn apart, scattered across the galaxy like debris from a shipwreck? And if it does survive, What will the sky look like when the collision is over? What will remain of the universe we thought we knew? Let's start with the good news. The solar system will almost certainly survive the merger intact. Not unscathed, not unchanged, but intact. The Sun will not collide with another star. Earth will not be vaporized in a catastrophic impact. The planets will not be ripped from their orbits and flung into the void. The odds of any of those things happening are so low that they are not worth losing sleep over. The reason comes down to scale. Space is big, unimaginably, absurdly, incomprehensibly big. The distance between stars is so vast compared to the size of the stars themselves that even when two galaxies collide, even when 1 trillion stars pass through each other, direct collisions are extraordinarily rare. Think of it this way. If you shrank the Sun down to the size of a ping-pong ball, the nearest star, Proxima Centauri, would be another ping-pong ball sitting roughly 3,000 miles away. That is the distance from New York to Los Angeles. Now imagine 2 handfuls of ping-pong balls, each containing hundreds of billions of balls, thrown at each other. The balls pass through like ghosts. Almost none of them touch. That is what happens when galaxies collide. The stars drift past each other, their orbits bent and scrambled by the gravitational field, but direct impacts are so rare that they might not happen at all. Astronomers have run the numbers. The chance of the Sun colliding with another star during the Andromeda Milky Way merger is roughly 1 in a few trillion. You are statistically more likely to win the lottery, get struck by lightning on the same day, and then win the lottery again. The solar system is not in danger of a direct hit. What it is in danger of is being moved, relocated, scattered into a new orbit by the gravitational chaos of the merger. And that is where things get interesting. Right now, the Sun sits about 26,000 light-years from the center of the Milky Way, orbiting at a speed of roughly 220 kilometers per second. It completes one orbit every 230 million years, following a relatively circular path through the galactic disk. That orbit is stable. It has been stable for billions of years. The Sun formed in this region of the galaxy, and it has been quietly circling the center ever since, passing through spiral arms, drifting above and below the plane of the disk, but always staying within the same general neighborhood. The solar neighborhood, astronomers call it, a region of space about 1,000 light-years across, where the density of stars is roughly average and the conditions are relatively calm. No massive stars nearby waiting to explode as supernovae. No dense star clusters where gravitational interactions could perturb planetary orbits. Just a quiet corner of the galaxy where a star can spend billions of years without anything dramatic happening. That stability is about to end. When Andromeda arrives, the gravitational field of the Milky Way will be distorted. Stars will be pulled, pushed and scattered into new orbits. Some will be kicked outward, flung into the outer halo where the density of stars drops to nearly zero and the distances between neighbors stretch to tens or hundreds of light years. Some will be dragged inward, pulled closer to the galactic center where the stellar density is higher and the night sky is crowded with thousands of bright stars. And some, a small but non-negligible fraction, will be ejected from the galaxy entirely, flung out of the local group at high velocity, destined to wander alone through intergalactic space for the rest of their existence. The Sun could end up in any of those categories. The outcome depends on the details of the merger, the exact trajectory of Andromeda, the timing of the close passes, and 1,000 other variables that we cannot predict with certainty. What we can do is run simulations, feed in the current data, let the computer model billions of years of gravitational interactions, and see where the Sun ends up in the majority of scenarios. The results are not comforting. In about 50% of the simulations, the Sun gets kicked outward, relocated to a new orbit somewhere between 30 and 100,000 light-years from the galactic center. That is 2 to 4 times farther out than where we sit now. The stellar density in that region is much lower. The distances between stars stretch to 5, 10, 20 light-years. The night sky from Earth, assuming Earth is still around and still habitable by that point, would be noticeably different. Fewer stars visible to the naked eye. The Milky Way, that bright band of light stretching across the sky, would be dimmer, narrower, less prominent. The galaxy would still be there, still holding the solar system in its gravitational grip, but it would feel more distant, less immediate, like we had been pushed to the outskirts of a city and were now living in the suburbs where the lights are dimmer and the neighbors are farther away. In about 12% of the simulations, the outcome is more dramatic. The Sun gets ejected entirely, flung out of the Milky Way, out of Milkomeda, out of the local group, sent wandering into intergalactic space at a velocity high enough that it will never fall back. 12%. That is roughly 1 chance in 8. Not a coin flip, but not a remote possibility either. If the Sun gets ejected, the night sky from Earth changes completely. No Milky Way, no galactic disk, no band of light stretching across the heavens, just a few faint smudges, distant galaxies millions of light-years away, barely visible against the blackness. The sky would be darker than anything any human has ever experienced, darker than the deepest ocean trench, darker than the inside of a sealed cave, and it would stay that way forever. The Sun would drift through intergalactic space for billions of years, slowly cooling, slowly fading, until it exhausted its fuel and collapsed into a white dwarf, and eventually into a cold, dead cinder, radiating no light at all. That is the worst-case scenario for the solar system. Ejection, exile. Wandering alone through the void with nothing nearby, no stars, no galaxies, no structure, just the endless empty blackness of intergalactic space stretching in every direction. But even in that scenario, Earth survives, the Sun survives, the planets stay in their orbits. The gravitational pull of distant galaxies is so weak that it does not perturb the solar system at all. From Earth's perspective, aside from the night sky, nothing changes. The Sun still rises in the east and sets in the west. The Moon still orbits. The seasons still cycle. Life, if it still exists by that point, continues exactly as it did before. The solar system becomes an island, isolated from the rest of the universe, but it remains a functional system, stable, predictable, indifferent to the fact that it has been cast out. The more likely outcome, the one that shows up in the majority of simulations, is that the Sun stays inside Milkomeda but gets relocated to a different orbit. Maybe farther out, maybe closer in, maybe on a more elliptical path that takes it swinging through the galactic disk at irregular intervals. The details vary, but the solar system remains bound to the galaxy. It does not escape. It does not fall into the central black hole. It just moves to a new address within the same structure. And from Earth's perspective, the main difference is the view. That view will change dramatically long before the merger completes. In fact, the changes will start within the next billion years, long before Andromeda gets close enough to distort the Milky Way's structure. Right now, Andromeda is visible from Earth as a faint smudge in the constellation Andromeda, roughly the size of 6 full moons laid end to end, but so dim that you need a dark sky and good eyesight to see it at all. Most people have never seen Andromeda with their naked eyes. It is too faint, too diffuse, too easily washed out by light pollution. But as Andromeda approaches, it will get brighter. Not because the galaxy itself is changing, but because the distance is shrinking. Light follows an inverse square law. double the distance, and the apparent brightness drops by a factor of 4. Halve the distance, and the brightness increases by a factor of 4. Andromeda is currently 2.5 million light-years away. In a billion years, it will be closer to 1 million light-years. The apparent brightness will increase by a factor of 6 or 7. The galaxy will no longer be a faint smudge. It will be a distinct oval disk, clearly visible even from suburban skies, large enough to span 10 or 15 degrees of sky, about 30 full moons across. In 2 billion years, assuming Earth is still habitable, Andromeda will dominate the night sky. It will be enormous, stretching across 60 or 70 degrees, more than a third of the sky from horizon to zenith. You will be able to see structure, spiral arms, dust lanes, star-forming regions glowing with the light of young blue stars. It will be brighter than the Milky Way, brighter than the moon on some nights, bright enough to cast faint shadows if you stand in a dark field far from artificial light. The sight will be breathtaking and deeply unsettling in equal measure. A galaxy, an entire galaxy, close enough to resolve into individual components, close enough to see that it is moving, changing, approaching. It will be a reminder, impossible to ignore, that the universe is not static, that the structures we think of as permanent are temporary, that the sky we grew up with is not the sky our descendants will inherit. By 3 billion years from now, Andromeda will fill the sky. Not metaphorically, literally. The galaxy will span more than 100 degrees, stretching from horizon to horizon in some directions, its central bulge glowing like a second moon, its spiral arms wrapping around the Milky Way's disk as the two galaxies begin to interpenetrate. The night sky from Earth will be unrecognizable. The Milky Way, that familiar band of light arcing overhead, will be distorted, warped, stretched into tidal tails that curve outward and upward. Andromeda's stars will mix with the Milky Way's stars, creating a chaotic tangle of light and dark, with bright patches where gas clouds are collapsing to form new stars and dark patches where dust blocks the view. The sky will be bright even on moonless nights, illuminated by the combined light of hundreds of billions of stars from two galaxies merging into one. And then, assuming anyone is still around to see it, the first close pass will happen, 4 to 4.5 billion years from now. Andromeda and the Milky Way will pass through each other, their outer regions overlapping, their stars drifting past like ghosts. For a few 100 million years, Earth will sit inside two galaxies at once. The night sky will be ablaze, thousands of stars brighter than Venus, dozens bright enough to cast shadows. The horizon in every direction glowing with the light of distant star clusters. It will be the most spectacular sky any planet has ever seen. And it will be temporary. After the first pass, the galaxies will separate, swing back around, and collide again. Each pass will distort the structures further, scatter the stars more widely, and funnel more gas toward the centers where the supermassive black holes sit. By the time the merger completes, 6 or 7 billion years from now, the sky will settle into something quieter, a smooth elliptical glow. Milkomeda. A single galaxy, large and old, filled with aging stars and very little gas. The spectacular light show will be over. The night sky will dim, and whatever remains of Earth will orbit a star in a galaxy that no longer resembles the one it was born in. But here is the thing, none of that matters to Earth. Not because it is not happening. It is happening. The galaxies are colliding. The solar system will be moved. The night sky will transform into something unrecognizable. All of that is real. But Earth will not be around to see it, not as a habitable planet, not as a place where life can exist. The reason has nothing to do with Andromeda. It has everything to do with the sun. The sun is getting brighter, not dramatically, not in a way you would notice from year to year or even from century to century. But over billions of years the increase is significant. The sun is a main sequence star, fusing hydrogen into helium in its core, and as it burns through its fuel, the core contracts slightly, heats up, and burns more efficiently. The result is a slow, steady increase in luminosity. The sun today is about 30% brighter than it was when it first formed 4.5 billion years ago. And it will continue brightening at roughly the same rate for the next few billion years. In about 1 billion years, maybe 1.5 billion, the sun will be bright enough that Earth's oceans will begin to evaporate. The surface temperature will rise, the greenhouse effect will amplify. The atmosphere will fill with water vapor, which traps even more heat, which evaporates even more water, and the cycle will run away. Within a few 100 million years, Earth will look like Venus, a scorched, lifeless rock with surface temperatures high enough to melt lead and an atmosphere so thick and toxic that nothing remotely resembling life as we know it could survive. That happens long before Andromeda arrives. 1 billion years from now, give or take, Earth will be uninhabitable. 2 billion years from now, it will be a dead planet. 3 billion years from now, it will be a baked cinder orbiting a star that is slowly swelling into a red giant. And 5 billion years from now, the sun will expand so dramatically that its outer layers will engulf Mercury, Venus, and possibly Earth itself. The planet will either be vaporized, consumed by the sun's expanding envelope, or it will survive as a charred remnant, stripped of its atmosphere, its oceans boiled away billions of years earlier, orbiting inside the outer layers of a dying star. So when we ask whether Earth will survive the Andromeda collision, the answer is yes. Technically, the planet will not be destroyed by the merger. It will not collide with another planet or get flung out of the solar system. The gravitational chaos of the collision will not tear Earth apart, but by the time the collision happens, Earth will already be dead. The sun will have killed it long before Andromeda arrives. The merger will rearrange the solar system, move the sun to a new orbit, scatter the planets slightly, and transform the night sky into something spectacular. But Earth will not be habitable to witness any of it. The story of Earth ends not with a collision, not with a dramatic cosmic event, but with the slow, inevitable brightening of an ordinary star. That is the unsettling part. The universe does not care about Earth. It does not care about life. It does not care whether we survive or go extinct or evolve into something unrecognizable. The galaxies will collide because gravity pulls them together. The sun will brighten because that is what main sequence stars do. Earth will become uninhabitable because planets orbiting stars that get brighter eventually become uninhabitable. None of it is personal. None of it is targeted. It is just physics playing out over billions of years, indifferent to the fact that for a brief moment in cosmic history, one small planet in one ordinary solar system, in one unremarkable galaxy, happened to host something that could look up at the sky and wonder what was going to happen next. And yet, for all that indifference, there is something remarkable about the fact that we can predict this at all, that we can look at a faint smudge in the sky, measure its motion, calculate its trajectory, and know with reasonable confidence that in 4.5 billion years it will collide with our galaxy. That we can run simulations of 1 trillion stars interacting gravitationally over billions of years and predict, with better than 50% accuracy, where the sun will end up when the chaos settles. That we can measure the sun's luminosity, track its slow brightening, and know that Earth's habitability has an expiration date measured in hundreds of millions of years. That knowledge does not change the outcome. It does not give us a way to stop the collision or prevent the sun from brightening or keep Earth habitable forever. But it does give us something else: perspective. The collision between Andromeda and the Milky Way is not the end of the universe. It is not even the end of our corner of the universe. It is a restructuring, a merger, two galaxies becoming one. Milkomeda will be larger, older, more stable than either of its parent galaxies. It will contain more stars, more planets, more opportunities for whatever comes next. And somewhere in the middle of all that, assuming we or our descendants or something we cannot yet imagine is still around, there will be a chance to witness the most spectacular cosmic event that has ever happened in the local group. A chance to see a galaxy collision from the inside, to watch the sky transform over millions of years from the familiar patterns we grew up with into something entirely new. To stand on a planet, any planet, and look up at a sky filled with the light of 1 trillion stars from two galaxies merging into one. That chance will not belong to us. We will not be here. Humanity, if it survives at all, will have moved elsewhere long before Andromeda arrives, to another planet, another star, another galaxy. Or it will have evolved into something so different from what we are now that calling it humanity would be a stretch. Or it will be gone entirely, extinct, replaced by something else, and the collision will happen without witnesses, without meaning, without anyone to care. That is the most likely outcome. The universe has been running for 13.8 billion years. Humanity has been around for a few 100,000. Civilization for a few thousand. The odds that we will still be here, in recognizable form, billions of years from now, are effectively zero. But the solar system will still be here. The sun will still be shining. Earth, even if it is no longer habitable, will still be orbiting, and Andromeda will still arrive, right on schedule, indifferent to whether anyone is watching. The galaxies will collide, the stars will scatter, the night sky will transform, and the universe will continue doing what it has always done, expanding, evolving, reshaping itself on scales so vast that human lifetimes are not even a rounding error. The Andromeda collision is not a threat, it is not a disaster, it is not even particularly unusual. It is what galaxies do. They form, they grow, they collide, they merge, and out of that chaos, something new is born. Milkomeda will be that something new, a galaxy that did not exist before. A structure built from the wreckage of two older structures. And somewhere inside it, unless the 12% chance of ejection comes up, the sun will still be orbiting. A single star among trillions, insignificant, unremarkable, carrying with it the remnants of a solar system that once hosted a planet where something briefly looked up at the sky and wondered what was out there. That planet will be gone by then. That something will be gone too. But the sun will remain, drifting through Milkomeda's halo, circling the merged galactic core, completing orbits that take hundreds of millions of years until the fuel finally runs out and the sun itself fades into darkness. And even then, the story does not end. Because the universe is patient, it has all the time in the world, and when one story ends, another begins, and even then, the story does not end. Because the universe is patient, it has all the time in the world, and when one story ends, another begins. So here we are, standing on a small planet orbiting an ordinary star in the outer suburbs of a spiral galaxy that is currently falling toward its neighbor at 110 kilometers per second. The collision will take billions of years to complete. The outcome is already written in the equations. And yet, from our perspective, from this brief moment in cosmic history where we exist and can look up at the sky and understand what we are seeing, none of it feels inevitable. It feels impossible. A galaxy, an entire galaxy, containing 1 trillion stars, moving toward us, not drifting, not wandering, moving with purpose, pulled by gravity across a void so vast that light takes 2.5 million years to cross it. And we are just here, watching, measuring, predicting, knowing that this collision has been in motion since long before Earth existed and will continue long after Earth is gone. That is the strangest part, not the collision itself, not the violence or the scale or the transformation that follows. The strange part is that we can see it coming, that we can point a telescope at a faint smudge in the constellation Andromeda, measure the blue shift in its spectrum, calculate its velocity, model its trajectory, and know with confidence that 4.5 billion years from now, that smudge will be here. That the quiet, predictable sky we grew up with is temporary, that the Milky Way is not a permanent structure, that the universe is not a place where things stay put. It is a place where things move, collide, merge, and become something new. And Andromeda is moving toward us right now, this very second, closing the gap by another 110 kilometers.